Hello everyone and welcome to the Coding Interview Jumpstart course. I just want to say that I'm very excited to have you here, and I honestly hope that this course will have a career-changing impact for you. In this course, we will together make the first steps in the exciting world of algorithms. If you have never learned anything about algorithms, don't be afraid or intimidated. Algorithms aren't as hard as people often consider them to be, and I am convinced that any programmer can master the art of problem solving and algorithms if he or she has the motivation to succeed. In fact, I believe that most of the algorithms can be very easy to understand if they are explained in a clear and simple way. Considering that I know how hard can the beginning be, because I have been in the same situation once, I have invested my knowledge and experience into this course to help you guys making the first steps towards mastering algorithms and bringing you one step closer to your dream job. So, my name is Branko and I will be your instructor in this course. Now I will quickly walk you through my story so we get to know each other. Currently, I'm a computer science student. I have done a 5-month internship at Microsoft in 2017 as a part of Office team, and this summer I'm starting my second internship. I've been also working as a tutor in an educational center for more than 2 years, where I am teaching algorithms and problem solving and preparing high school students for national and international programming competitions. Together with my 3 friends, we have won and participated on several hackathons. I love competitive programming and I have participated and won prizes on several competitions like the International Olympiad in Informatics, the Balkan Olympiad in Informatics, and the ACM ICPC programming competition. I have also created problems for algorithmic competitions for the National Olympiad in my country and also for the Bubble Cup Finals, which is an international programming competition organized each year by Microsoft. And I have worked as a full-stack developer on several freelance and private projects. So guys, that was a quick intro about my story because I wanted to introduce myself to you guys. So again, thank you guys for choosing this course and I am really honored to be your instructor. Thanks for watching and see you in the next video. Hi everyone, in this video I will quickly walk you through the sections of this course for you to get a better feeling what's this course about. First, we will start with a very essential thing in the world of algorithms, and that's algorithm analysis. We will see why do we have to analyze our solutions, what is asymptotic notation, and a very specific type of notation called the big O notation. And finally, we will analyze the time and space complexity of some examples. In the next section, we will learn about sorting algorithms, and we will explore different ways of sorting a sequence of objects. We will learn about bubble sort, selection sort, insertion sort, and then we will learn about more complex and more efficient algorithms like merge sort, quick sort, and counting sort. Then in the next section, we will talk about a fundamental searching algorithm called binary search. Binary search is a must-know algorithm, and we will learn about the standard idea and implementation, but we will also learn about binary search variations like finding the first or last occurrence and also counting the number of occurrences of some target value. And finally, the last section is a special bonus section. Here I will post detailed interview problems solutions. And I encourage you to post some interesting problems in the discussions, and each 1 to 2 weeks I will choose new problems and post a new video in this section where we solve those new problems. So that's it guys, thanks for watching and let's begin with the course. Hello guys and welcome. In this section, we are going to talk about algorithm analysis. For some of you, this will be your first step into the world of algorithms, and I hope you will understand why is this such an important topic. In the following lectures, we are going to focus on several things. First, we will learn about the importance of analysis and why do we have to analyze our solutions. Then we are going to focus on asymptotic notation, which is basically a language that allows us to analyze program running time by identifying its behavior as the input size for the algorithm increases. After that, we will focus on a specific type of notation called the big O notation, and we will use the big O notation to compare different algorithms. Finally, we are going to practice these concepts by calculating time and space complexity of some given algorithms. At the end of this section, you will be able to analyze and compare different algorithms and to decide which one is the best fit for a given problem. So let's begin, guys. If you are new to algorithms and problem solving, you are probably wondering why do we even need to analyze our solutions. I mean, we can just solve the problem, write down the code, and everything seems fine. For every test case that we manually try, our program gives the correct output. So why bother analyzing algorithms? Let's look at the following scenario. You found yourself on a programming interview and you are given this problem. For a given integer n, determine whether the number n is prime or not. So we know that the number n is prime if it is only divisible by 1 and itself. So an easy solution comes to mind that we can just check every number from 2 to n minus 1, and if there exists a number that n is divisible by in that range, we know that n is not a prime number. Otherwise, n is a prime number. So let's look at the code. Here we have a function called isPrime that takes as input an integer n and returns true or false depending on whether the number n is prime or not. In the first 3 lines we have this if statement which basically checks if n is less than 2 and immediately returns false. We can do this because we know that the first prime number is the number 2, so if n is less than 2, it's for sure it's not a prime number. Then we have a for loop that iterates from 2 to n minus 1 and checks whether n is divisible by the current number I. If n is divisible by any number in this range, we know for sure that n is not a prime and we can immediately return false from the function. Otherwise, when the for loop ends and we don't find any number that n is divisible by in this range, we know that n is a prime number and we can return true, because the only two divisors of n are 1 and n itself. Let's look at our main function. In the first line in the main function is just declaring a new scanner object which we will use for reading from the standard input. The next line reads the next integer and stores it in the variable n. And finally we call our function isPrime with the argument n, and we print the result to the console. We have several more lines, for example this line and these lines here. You don't have to worry about these lines. I use these lines just to print out the total execution time of our program, so we can compare the differences in the running time. On the bottom of the page I have written some prime numbers so we can check whether our algorithm works correct. So let's try 7. Okay, it returns true, so this means that 7 is a prime number, which is indeed correct, and this is our total running time. It's almost constant. Let's try 101. Also true, also correct, prime number, and a bit more time. let's try a number which is not prime for sure. For example, 10 is not prime number because it is divisible by 5, and it returns false, which is correct. Now let's try this big number, which is 1,000,000,007. Let's try this, and we can see something interesting here. Here we have a delay. When we input the number, we have to wait exactly this much, 3.5 seconds, for our program to finish, and it returns true, which is correct. But here we can see that our algorithm might not be the most efficient one, because we had to wait 3.5 seconds, which is not much time. But let's look what happens if we input an even larger prime number. So let's try with this number. And what happens? Let's see. We get an exception that says input mismatch exception. This is a problem caused by this number not being in the range of an integer. So this number is larger than the maximum integer we can store in a 32-bit data type in Java. So we have to change our variable and our function so that it accepts a 64-bit integer. So let's do that. We have to change here, and we must say that we want the next along from the standard input, and also in the function declaration along, and also here, because we loop from every number from 2 to n-1, which can also overflow if it stays an integer. Let's try now. First, I want you to show something interesting. If we again try 1,000,000,007, let's look at the result. Here will something interesting happen. We are waiting a bit longer, as we see, and now we got a result. And it says we waited almost 12 seconds, which is a lot bigger waiting time than in the previous example, where everything we change is we didn't change anything in our algorithm, but we have changed the data type from int to long. And this is natural. This increase in running time is natural, because in our previous example we had the same number of operations in our program, but we used a 32-bit integer, and now we are using a 64-bit integer. So that means that every operation is 2 times more expensive. So we can expect 2 times or even more than 2 times bigger running time, greater running time. Now let's try the biggest of these prime numbers in the list, and let's see what happens. Now we wait, and we wait, and we wait, and believe me, we have to wait a lot more than we expect. I think this here we could wait for hours or for days for this program to finish. So this is why we need to analyze our algorithms, because we have to know how efficient our algorithm is, so we can compare it to other algorithms and find the best one for our problem. So what do we have to do now? We now know that our algorithm isn't so efficient, so we have to optimize it. We have to find something more clever, so that we decrease the number of total number of operations in our algorithm. And so let's look how to optimize our algorithm. For each number, we can divide its divisors into two groups. The first group contains the factors which are less than or equal to the square root of n, and the second group contains all the numbers that are greater than the square root of n. Let's look at this on an example. For example, the number 36 has the following divisors: 1, 2, 3, 6, 9, 12, 18, and 36. Let's divide them into two groups. 6 is the square root of 36, so everything left from this bar belongs to the first group, and everything right belongs to the second group. And now let's look at this fact. 36 can be written as a product of two numbers, where the first number belongs to the first group and the second number belongs to the second group. For example, 1 times 36 is equal to 36. 2 times 18 is equal to 36. 3 times 12 is equal also to 36, and if the number has a square root, which is an integer, we can also write 6 times 6 is equal to 36. Okay, we will use this fact to optimize our algorithm. But how? We know that the factors come in pairs. 1 is paired with 36, 2 is paired with 18, 3 with 12, and 6 with 9. So we can just check the numbers until the square root of n, and if we don't find a number that n is divisible by until the square root of n, we know for sure that we won't find any divisor which is greater than the square root of n. Because if there exists a divisor in this range which is greater than the square root of n, this means that he also has a pair in the first group which is less than or equal to the square root of n. So we don't need to check the numbers until n minus 1. We can just check the numbers until the square root of n. We can write like this: int limit is equal to math square root of n. And let's cast this to an integer. And here we have to go I is less than or equal to the limit, because we have to check everything which is less than or equal to the square root. And let's try our program again. Here we can use long or integer, because the square root, it's the same, because the square root won't overflow the integer. It can be saved as an integer. Let's look at our examples now. Where are examples? Here. Let's look at 1,000,007,000. Let's run the program. Check 1,000,007,000, and we see something great here. We get the correct result, and it in almost constant time. Wherein our previous algorithm, it took around 10 seconds to finish this example, this test case. And let's look at the biggest these prime numbers in our list. Our algorithm didn't even manage to finish this test case. But let's try this time. We get a result in almost immediate time, and it's a correct result because this is a prime number. Let's just test some number that is not prime to convince us that our algorithm is correct. For example, 100. Yeah, it says false, and 100 is divisible, for example, with 50. Or maybe 12, which is divisible by 6, and it also says false. And here we see the power of algorithms. We changed our algorithm, optimized it, we noticed some observations, some smart observations, so that we don't have to iterate all the way through n, and we iterated just to the square root of n. And now, instead of our algorithm iterating n times, we just iterate square root of n times. So this means that in the worst case, our algorithm will execute around square root of n operations, where our first algorithm in the worst case executed around n operations. And this is a big improvement. I have to mention that today's computers can execute around 1 billion operations in a couple of seconds. So this is the reason why our first algorithm, which took n operations, finished the test case 1,000,000,007 in around couple of seconds, 3-4 seconds. And this is very important to know, because we can calculate the total number of operations our algorithm will execute, and we can see if this is a much bigger number than 1 billion. We know that we have to optimize our algorithm, and this solution won't work for bigger inputs. As we saw in our algorithm, if we input this number, which is much greater than 10 to the 9th, our algorithm didn't have the chance to finish because it was really slow. It had to execute almost this number of operations. When we optimized our algorithm and we took down the number of operations to around the square root of n, it became much faster, because square root of 1 billion is a much smaller number, and our program finished almost immediately for this number of operations. So in this example, I wanted to show you that it is important to analyze your algorithms to know how many operations your algorithm will execute in the worst case, because if you don't take care about the total number of operations, you will end up with inefficient algorithms, and that will work just for small test cases and won't work for bigger test cases. So let's recap. The most important thing is that average computers today can execute around 1 billion operations in a couple of seconds. And when we write some program to compute some result, we want it to finish in couple of seconds. So this means that the total number of operations our algorithm executes in the worst case must be less than or around this number. So if we notice that our algorithm will execute 10 to the 10th power of operations, this means that we have to find a better algorithm, because this one won't finish in a couple of seconds. Inefficient algorithms can take hours or even days or months to finish. So we have to analyze our algorithms, determine the total number of operations, and optimize it, or even change to a completely different algorithm which is faster if we notice that our previous algorithm isn't good enough. In the next lectures, we will focus on how to determine the total number of operations of an algorithm and how to use the asymptotic notation to estimate the total number of operations. Okay, thank you guys, and see you in the next lessons. Hello guys, and welcome. In this video, we are going to talk about asymptotic notation and continue our journey with algorithm analysis. The running time of our program depends on several factors. The most obvious factor is the computing power and speed of our computer. The next factor is the programming language our program was written in. This is because some languages are faster than others. And also the compiler, which translates the source code into machine code, plays a big role, because some compilers include big optimizations of the code while translating. These first three factors can impact the total running time of our program, but they are not directly connected to the algorithm that we use in the program, and we can consider them as external factors. The more important factor is the maximum number of operations our algorithm will execute. This obviously depends directly on the algorithm we choose to use, and we want this number to be as low as possible, so that our program can complete faster. Now let's look at this function and try to determine what is the total number of operations executed here. So let's start with the first line. Let's look at the first line. Here we have just one assignment operation, a equals to 5. In the next line we have a for loop. A for loop has 3 parts. The first part is just an initialization where we set I to 0, and this is only one operation because it's only done the first time. Then we have the condition, and on each iteration we check whether this condition is true or false. Because we have n iterations of the for loop, we have n plus 1 comparisons here, because the first n times this condition will return true, and the n plus first time when I is equal to n, this condition will return false and the loop will terminate. So hence we have n plus 1 operations. And finally here we have the incrementation, and each time I is incremented by 1, and we have exactly n iterations, so we have n increments here. So the total number of operations for this line is 2n plus 2 when we sum these 3 up. The next line is also a for loop, and it would be great to remember that if we have a for loop which iterates n times, then this for loop will execute 2n plus 2 operations, because we explained here what are those operations. So this inner loop is exactly the same as the outer loop. It has exactly the same number of iterations, so the number of operations is also the same, 2n plus 2. This block inside the loops has 3 operations, 1 multiplication, 1 addition, and 1 assignment. Okay. Next, this line b is equal to 0, this is just one assignment operation. Now another for loop. We have one operation for the assignment, and here we have 3n plus 1 condition checks. Why is this? Because the for loop will iterate exactly 3n times, so 3n times this condition will evaluate to true, and the 3n plus first time this condition will evaluate to false, and this is where when I will be exactly equal to 3 times n. And here, because of 3n iterations, we have 3n increments, and this is 6n plus 2. Here we could have also used the knowledge from earlier, where we stated that every for loop that has n iterations will have 2n plus 2 operations. So we know that our for loop will have 3 times n iterations, so if we multiply 2 times 3n, it will be equal to 6n plus 2 operations. Inside the for loop we have 3 operations: multiplication, addition, and assignment. And finally, in the last line we have 1 addition and 1 return statement, which is equal to 2. Now let's write all this down. If we denote the total number of operations as t of n, where n is the input to the function, we can write the following. We have 1 operation for the first line. Then we have 2n plus 2 operations for the for loop. Then we have 2n plus 2 operations for the inner loop, but this inner loop will repeat itself on every iteration of the outer loop. So this means for every iteration of the outer loop, we will execute exactly 2n plus 2 operations for the inner loop. So this means we have to multiply the number of iterations of the outer loop, which is n, because the outer loop iterates from 0 to n minus 1, times the number of operations of the inner loop, which is 2n plus 2. And the next line, we have these 3 operations, but these 3 operations are inside 2 nested loops, where each loop iterates exactly n times. So for each iteration of this loop and each iteration of this loop, we have 3 operations here. This means that we have to multiply 3 times n squared, because 1n for the inner loop and 1n for the outer loop. So 3n squared here. Then we have one assignment here, and 6n plus 2 operations for this line, for this for loop. And what do we have here? We have 3 operations inside the loop, but these 3 operations repeat themselves for every iteration of the loop, and the loop has 3 times n iterations. So we have to multiply 3 times 3n. And finally we have these 2 operations in the last line. And this is it. We just have to sum everything up and multiply the parentheses. So let's do this. We have 1 plus 2n plus 2 plus n times 2n is 2n squared, plus n times 2 is 2n, plus 3n squared, plus 1, plus 6n, plus 2, plus 3 times 3n is equal to 9n, plus 2. And we have just to sum all the corresponding terms. We have 2n squared and 3n squared, which is equal to 5n squared. Then we have 2n plus 2n plus 6n plus 9n, which is equal to 19. 19n, and plus we have 1 plus 2 is 3, plus 1 is 4, plus 2 is 6, and plus 2 is 8. And here we have the total number of operations of our function: 5n squared plus 19n plus 8. And on this example we can see that this process can be quite painful. We see that we have a lot of calculations, summations and multiplication, and this is just an easy example. Imagine what it would be like for a much harder example, much more complicated code. So instead of doing these calculations every time, we want to estimate the total number of operations of our algorithm. But how can we do that? Now let's look at this graph. This graph shows us how much faster does the function 5x squared grows in comparison with the function 19x plus 8. This tells us that when n is huge, the term 5x squared is much greater than 19x plus 8. So this means that the highest term is much greater than everything else when n is huge. So this gives us an idea how to estimate this function. We can ignore everything besides the highest term, so every less significant term we ignore, and we can also ignore the constant that is located with the highest term, and we are just left with this one, with n squared. This n squared represents the rate of growth of our algorithm. This is basically an estimation of how much operations does our algorithm execute depending on the input size. This n squared tells us that the bottleneck of our algorithm is here, in these two nested for loops, because these two for loops have n iterations, and when n is multiplied by n, we get the rate of growth of n squared. So here is the part of code that we have to optimize. By dropping the less significant terms and the constants, we are using asymptotic notation, and there are three types of asymptotic notation called big O notation, big theta notation, and big omega notation. And in this course we will focus on big O notation as the most commonly used one. We will use the big O notation to estimate the program running time and compare different algorithms and choose which one is the best for a given problem. So to recap, guys, we calculated the total running time precisely for this algorithm, and we saw that this can be a painful process, but also by looking at this graph we concluded that we don't have to calculate the exact total number of operations, but we can just determine what is the rate of growth of our function to get an estimation of the total number of operations. And we saw here that we can get the rate of growth by dropping every less significant term and dropping all constants and just leave the most significant term, which estimates our algorithm. And also we mentioned that there are three types of asymptotic notation: big O, big theta, and big omega. And in the next lessons we will focus on big O notation and determine time complexities of some given algorithms and write them down in big O notation. So thank you guys, and see you in the next lessons. Hello guys, and welcome. In this lecture we are going to talk about big O notation. We will explain what is big O notation, what does it describe, and how to use big O notation to determine whether an algorithm is efficient or not, and to compare different algorithms and find the best one. So big O notation is used to describe the performance or complexity of an algorithm. Big O specifically describes the worst case scenario, and it can be used to describe the execution time required or the space used by an algorithm. For example, let's use a program running time function t of n to be equal to 5n cubed plus 7n squared plus, let's say, 3n plus 8. So the total running time of some program can be described by this function. So what do we want to accomplish is that we want to determine an upper bound for this function so that we can successfully estimate the total running time without calculating all these components. So as we saw in the previous lecture, we can drop all the less significant terms and leave just the most significant one, and also drop the constants, drop this 5. So we can get that this function is O of n to the third power. And what we've got here is that we say that this n to the third is an upper bound for this function. So we basically said that t of n is less than or equal to some constant k times n to the third power for a sufficient large n. So for a large enough n and some constant k, t of n will be less than or equal to k times n to the third power. So we have successfully set an upper bound for our total running time function, and we now know that in the worst case our program will execute this much operations. So in the general case, if we have some function t of n and we say that it is equal to O of f of n, where f is some function. This basically means that t of n is less than or equal to k times f of n, where k is some constant. So for a large enough n and a constant k, k times f of n is an upper bound for the total running time function. How could this look like on a graph? If we have a graph and we draw these two functions, it could look something like this. Our t of n function, for example, and our k times f of n function. It could look something like this. So this is k times f of n, and the blue function is our t of n function. So basically, for every n which is greater than this point, we will have the condition that k times f of n is greater than t of n. So this is an upper bound for our function. Now we will look at orders of some common functions that we will see throughout this course. So when we say that an algorithm is O of 1, we call that algorithm constant algorithm because it finishes in constant time. These algorithms probably contain just some formulas or calculations, and they probably don't contain any loops in it. If we have running time of log n, we call these algorithms logarithmic. Famous example that we will later see in more detail is binary search, which has time complexity O of log n. Also we have linear time algorithms which have O of n time complexity. These are maybe some algorithms that have only one loop where we iterate through the whole array, and they are called linear because we examine every entry of the array. Also we have O of n times log n algorithms which are called linearithmic. After that we have n squared algorithms which are called quadratic, and we have cubic algorithms. And if our complexity is c to the nth power, where c is some constant number, we call these algorithms exponential algorithms. And if our complexity is O of n factorial, we call this factorial algorithms. These two last examples are very inefficient types of algorithms, and we want to avoid them. An example of an exponential algorithm could be a recursion that is exploring every state. A factorial algorithm could be an algorithm which is exploring every permutation of some array. We know that an array has, or a sequence has, an n factorial permutations, so if we explore every permutation, this means that the total time complexity will be of n factorial. So to quickly recap, if we say that our running time function t of n is equal O of f of n for some function f, this basically means that we have an upper bound for our function, and our function is at most k times f of n, where k is some constant. So for large enough n, so for example from this point and onwards, we know that k times f of n is always greater than or equal than t of n. So k times f of n is a great estimation of the worst case running time of our algorithm. And finding the big O complexity of some function is pretty easy. We just drop all the lower terms and drop the constants, and we just remain with the highest term, n to the third power in this example. So for the big O complexity, all that matters for the total running time of the program is the highest term, the bottleneck of the algorithm. So, because when n is huge, this highest term will be much bigger than anything else in the function. In the next lecture, we are going to practice what we learned about big O complexity, and we will try to calculate the time complexity of some examples and describe them in big O notation. The beginning in algorithms is probably the hardest. I know it can sound scary, everything about the algorithm analysis and these big O notations, but this is pretty intuitive, I think. We ignore anything less than the higher term, than the highest term, and we drop all the constants, and we are just interested in this factor, in this n to the third, so in the highest term in our function. So basically this is all about big O notation. Big O notation gives us an upper bound for our algorithm. See you guys in the next lecture, where we are going hands-on with time complexity and big O notation. Hello guys, in this video we will go through some examples and we will try to determine their total time complexity. Now that we know about big O notation and we know that the rate of growth of our algorithm depends on just the highest term, and it doesn't depend on any constants or any lower terms, we now have to determine for each of these functions just the highest term, which is the bottleneck of our algorithm. And we'll exactly try to do this and represent our running time in big O notation. So let's begin with the first function. Here we have a function which is called hasDuplicates, which takes as input an integer array and returns a boolean. Basically, this function returns true if our array has duplicate elements, and returns false if every number in this array is unique. So let's look how we are going to determine the total time complexity. In the first line, we just have some constant number of operations, and each time we have constant number of operations, we can write this as O of 1, which means constant. We are not exactly interested in how many operations, 1, 2, 5, 10 or 100. This means that just here we have some number of constant operations, so we don't have any loops or anything like that. In the next line we have a loop which iterates from 0 to n-1 and increments by 1, so we know that this is O of n because it has n iterations. Next we look at the inner for loop, which has the same number of iterations, and we also write down O of n. Next, inside these for loops we have some if statement, and here we have just some comparisons. So these are just constant operations, so we write O of 1. And inside the if statement we have also O of 1 because of the return statement, which is just constant operation. And finally the last line is also O of 1. So now we have to look where could our highest term be in this function. We see that we have these two lines constant operations, and we see that we have these two for loops, and this is the part of code that we should worry about. So here we have O of n operations, but inside every of these iterations we have another O of n iterations, and inside this O of n we have some constant number of operations. So we can write that the total time complexity of this algorithm is O of n, because of this O of n operations, times O of n because this, and times, we can write times 1 because of these two constant operations, but we know that multiplying by 1 doesn't change anything, so the total time complexity is O of n squared for our algorithm. And this basically means that the bottleneck of our algorithm are these two for loops, because when these two n iterations multiply we get the n squared time complexity. So the total number of operations in this algorithm will be around n squared. We know for sure that the total number of operations will be less than or equal to some constant k times n squared. And this is a great estimation of the speed of our algorithm. Let's move on to the second example. We have a function called matrix sum, which takes as input two-dimensional array of integers and returns an integer which is the sum of every entry in our matrix. We denote as n the number of rows and as m the number of columns of our matrix. And these are just O of 1 operations. And here we have also some assignment which is O of 1. Now let's look at the for loops. We have the I for loop iterates from 0 to n minus 1 and increments by 1, which is O of n. The inner for loop j increments from 0 to m minus 1 and it increments by 1, which is O of m, because we have m iterations. And inside the for loops we have just some additions and assignments, which is, as we know, constant, which we write as O of 1. And the final line is also constant O of 1 because of this return statement. So immediately we see that the bottleneck are these two for loops, and let's write down the total time complexity. We have O of n operations here, and we have O of m operations inside this outer for loop. So the inner for loop has O of m operations, so we multiply this, and we could multiply by 1 because of this constant operations, but it doesn't change anything, so our total time complexity is O of n times m. And this is the first example where we can see that our running time can depend on multiple variables. It doesn't have to depend only of some variable n, because we see that in this case the total running time depends on the number of rows of our matrix and the number of columns of our matrix. Okay, so let's move on to the next example. We have a function called f, takes integer n as input and returns some integer. So here in the first line we have constant number of operations, and next we have two nested for loops. And this is a bit trickier example because we have n iterations here, which is O of n for sure, but the inner for loop makes a little bit of problem because it iterates from 1 to I. So it doesn't depend on n, it depends on the current value of I. So how are we going to solve this problem? We can just write here O of I and multiply this and say that our time complexity depends on some I, because the I is just a variable here which changes. It's not an input to our algorithm. We have to write our running time in terms of n. So what are we going to do here? Let's calculate the total number of operations executed in the inner for loop. So when I is equal to 1, j will iterate from 1 to 1, which is 1 iteration, plus when I increments to 2, j will iterate from 1 to 2, which are 2 iterations. When I is equal to 3, j will iterate for 3 iterations, and so on until finally I is equal to n. J will iterate from 1 through n, which is total of n operations. And so we know that this is how many times the inner for loop will iterate. So we know that this is just the sum of the first n numbers, and we can write this down as n times n plus 1 divided by 2. And we can write this as n squared plus n divided by 2, and we can write this as n squared divided by 2 plus n divided by 2. And here we see that inside these for loops we have just some constant operations, and by calculating the total number of operations executed by these two for loops, so the inner for loop will exactly iterate this much times, and inside each of these iterations we will have some constant operations. So we know that these two nested for loops will execute this many operations. So we can just take out the highest term, which is n squared, and ignore the constant, which is 1/2, and we can write down that these two nested for loops will have running time of n squared. Okay, this was a bit tricky. You just need to know that we don't need to multiply this by n for every iteration of this outer for loop, like we did in our previous examples. For example, n times n. Here, because here we calculated the total number of iterations of the j loop, the inner loop, depending on the outer loop. Because j will iterate all the way through I, we had to come up with this formula and calculate the total number of iterations. We had no other way to do this. So we know that this is the total number of operations of these two for loops, and we can ignore everything besides this n squared, because this is the highest term, and we ignore the constant. So we can write that these two for loops have time complexity of n squared. Some of you have probably thought that this has running time less than n squared, these two for loops, but as we see, j iterates first. The inner for loop will make 1 iteration, then 2, then 3, then n, which is n squared divided by 2 plus n divided by 2, and we just take the highest term, which is n squared. So let's move on to the next part of code. Here we have an easy for loop which iterates from 0 to n minus 1, because I is less than n, and we know that this is of n. Inside it is of 1, because constant number of operations. So let's look the next for loop, which iterates from 0 to 99, because I is less than 100. And we know that here we have 100 iterations, and inside we have constant number of operations. But is it correct to write here of 100? This 100 will always be the same. This is just a constant. It doesn't depend on any input to our algorithm. So instead of writing of 100, here we will write of 1, because this is how we denote constant number of operations. It doesn't matter how large n will be. N could be billions or even more. We will always execute here exactly 100 operations. So this is just a constant number. It doesn't depend on the input of the algorithm, and it is always the same. So we write of 1. So the total number of operations for this for loop is of 1 times of 1, which is also of 1. And finally, we have of 1 for this return statement. So let's look at the total time complexity. So what is the bottleneck of our algorithm? We have of 1 operations here. We calculated that these two for loops have total time complexity of n squared. This for loop has time complexity of n times of 1, which is of n. And this for loop is just of 1, because it's a constant number of operations. And also this line is of 1. So what is the bottleneck? What is the highest term? We just have to identify the highest term, and this is for sure this of n squared. So we can write the total time complexity is of n squared. So let's move on. Now let's look at this example. Here we have a function called g, which takes n as input and returns an integer as output. In the first two lines we just have some constant operations. we can write O of 1. But now for the first time we have a while loop, and we have to calculate the total number of iterations of this while loop. This is obviously a bit harder than the for loop, because in the for loop we have where the I starts and where does it end. But here this while loop will repeat until I drops to 1 or less. So each time when this condition is true, it will continue the iteration. So let's look how we can solve this. We know that I starts at 10 from this line, I equals equal to n, and each time we see that I is divided by 2. So at each iteration I will be 2 times smaller than in the previous iteration. So here we know that in the next iteration I will be equal to n halves, then in the next iteration I will be equal to n divided by 4, and in the next iteration to n divided by 8, and then n divided by 16, and then n divided by 32, and so on until I drops to 1. So when I drops to 1, this condition 1 is greater than 1 will evaluate to false, and the while loop stops. So we just have to determine in how many iterations will I drop from n to 1, where in each iteration we divide I by 2. Maybe you start to recognize this from some math knowledge, that this is basically equal to the logarithm to the log with base 2 of n. Basically the logarithm says this log 2 with base 2 of n tells us how many times do we have to divide I by 2 until we reach 1, and this is basically the solution for our problem. So it would be great to remember this, because we will encounter logs, especially with base 2, in the next lessons of our course, because there are a lot of algorithms that include the log n factor in their time complexities. And in further lectures we won't even be writing here the base 2, because in computer science it is basically accepted that when you write log n, we know that this is the log with base 2 of n. So now that we know this, we can denote that this while loop has time complexity of log n, because it will iterate around log n times, and in each iteration we have some constant operations. And finally we have O of 1 for this return statement, and the total time complexity is now pretty easy. We see that this is the highest term, and the total time complexity is of log n, where log is with base 2, but we agreed that in the further videos and in the rest of the course we won't be writing the base, because it will be the default base for our logarithms. And let's see one more example. This will be a pretty standard example. We have a function called union, which takes as input 2 arrays of integers a and b, and basically returns another array of integers which is the union of these 2 arrays. So it is basically these 2 arrays concatenated. So in the first line we have one assignment which is constant, and also in the second line constant number of operations, and also here we have some assignments which is also constant, and also in the next line. So these first 4 lines are pretty easy for time complexity. So we are interested in these 2 for loops. Let's look at the first for loop, which will iterate from 0 to n minus 1, which is of n iterations, and inside we just have some array access, which is O of 1, and also array access and some assignment. So this is O of 1, and this is also O of 1. Let's look at the next for loop. I goes all the way from 0 to m minus 1. So here we go to m, which is O of m. And the same story as in the previous for loop. This is O of 1, array access is constant, and also O of 1. And the final line is O of 1. So what do we have here? We have a lot of constant operations. Here we have O of n, and here O of m. So what will be the total running time? This for loop has O of n iterations, and inside each of a iteration we have constant operations, so the total running time of this for loop will be O of n because of the constant operations inside it. And similar story for this for loop, O of m times 1, which is also O of m. But what is the total time complexity? We have two separate for loops, one which iterates to n and has O of n total time, and another for loop which iterates to m and has O of m time. And what is the higher term between those two? We don't know, because both of them are inputs to our function. So what do we do now? If we write O of n, it would be a wrong estimate when n is small but m is huge, because this for loop will take much more time than this for loop. So this isn't correct. If we write O of m, this wouldn't be correct in the opposite example where m is small but n is huge. So this isn't also correct. So what is the correct time complexity in this example? We can write O of n plus m. So this is the first time that we see a plus in our time complexity, but we have to do this because when n is huge, the sum will also be huge, and when m is huge, the sum will also be huge. So we have to take the sum of those two separate parameters. So this is the total time complexity. So in opposite to the examples we solved above, where we have two nested for loops, we multiplied the time complexities for those two for loops, the running time for the outer for loop times the running time for the inner for loop. But here these two for loops are not nested, they are separate and parallel, so we just add those two times up. So this is it, guys. So that's it for this lecture, guys. I hope you enjoyed solving these problems, and I hope you learned something new, and that now you have a good foundation and good knowledge about how we are going to determine the time complexities throughout this course, because for every new algorithm that we are going to learn, we will analyze it, we will determine its time complexity and space complexity, and we will compare it to other algorithms. So I want to emphasize that this is a really important topic, because the knowledge we learn here we will be using throughout the whole course. When we are learning new algorithms, we will determine their time complexities and compare them to other algorithms, and we will check what is the most efficient one. And so thank you, guys, and in the next lecture we are going to practice some examples similar like in this video, but in that video we will focus on determining the total space complexity our algorithm use. So in the next video will be similar to this one, but in that video we'll focus on determining the space complexity of our algorithm. So what is the estimation of the total space our algorithm needs to run. So thank you, guys, and see you in the next lectures. Hello, guys, and welcome. In this video we are going to estimate what is the total space required by our algorithms. So how to do this? This is the first time we talk about space complexity, but you don't have to worry because it is almost the same as calculating the time complexity of some algorithm. And if you got a good grasp of time complexity in the previous videos, now this will be really easy for you. So what is the space complexity? If we denote the total space required by some algorithm as S of n, where S is the function for the total space required and n is the input parameter, and if we have some function like this, 5n cubed plus 3n squared plus 16n plus 10. This is the total space required of our algorithm. But to avoid all these calculations, similar to time complexity, we want to estimate what is the total required space by our algorithm. And we can do this with big O notation. So we will do the same thing as when calculating the time complexity, and that is that we need to drop every less significant term. So we can see that n cubed is the most significant term. So this is the only thing that matters in this function. And we can also drop the constant. So we can write that this function is O of n cubed. And we will say that for the algorithm that has this total space, we can say that its space complexity is equal to O of n cubed. So let's look at our examples and try to determine space complexity for these functions. So let's look at the first example. When we are trying to determine the total space, we have to watch out for every new variable declaration. So here we have one integer and here another integer, and inside the for loop we have an integer I. So how much space does an integer require? We can write for each of these integers that it requires O of 1 space. And why is this? Why can we say that an integer is O of 1? Basically we are saying that an integer is constant space. This is because that an integer is always 4 bytes in memory. It always uses 4 bytes, which is 32 bits in Java. So despite how big is this number, so this number n could be 1 billion or could be 16, the integer variable will always use 4 bytes of memory. So how much space does this variable use doesn't depend on the value it takes. So it depends on the variable type. So we can say that an integer is O of 1 space. Here we have also another integer which we know is constant space, and we write this as O of 1. And here inside the for loop we have the integer I, and we will denote this also as O of 1, constant space. So what is the total space of this algorithm? We just have to look at the space complexity of individual parts, this, and this one, and take the most significant one. In our example, every variable takes O of 1 space, so the total space complexity of this algorithm is constant, and we write this down as O of 1. So this is great because our algorithm doesn't use any extra space. We have the total space complexity is O of 1, and we aim for these situations. So let's look at the second example. In the second example, we have an integer array as a parameter, then we have one integer, another array, and one more integer. So let's look at the individual complexities. If we denote the length of this array as n, as we did in this line, we can say that this array has space complexity O of n, because it consists of n integers, and each integer is O of 1. We know that this array uses O of n space. So what about this integer? We know that this is O of 1. And the next line, we have another array which has the total size of 2n. So would it be correct to say that this array uses O of 2n memory? So here we apply the same rules as in time complexity, and we need to drop the constant. So we won't write that this array uses 2n memory, we will write instead that it has space complexity O of n, because the constants don't matter. And here we have one more integer, which is O of 1. And that's it for this function. We have two arrays with complexity O of n and two integers with complexity O of 1. And the highest terms are these two. So we could say we could add them up and we could get 2n. So, but the same, we want to apply the same principles as here. We don't need to write the 2, which is a constant, so we can only write, we can write that the total space complexity is just O of n. This means that our algorithm uses linear space. So let's move on to the next example. Here we have a matrix as input, and if we denote the number of rows of the matrix as n and the number of columns in the matrix as m, we can write that the space complexity of this matrix is n times m. So we have n rows and m columns, and so we have our matrix consists of n times m integers, and each integer is O of 1 space, so we don't need to multiply by 1. So this is the space required for this matrix. Next, here we have one integer, and also in the next line, and also in the next line. 3 integers which all have constant space. And in these two for loops, we have two variable declarations which are both integers, so we can write this is O of 1, this is also O of 1. And inside the for loops we have just some assignments and additions and array access. So we don't have any new variables. Next, in this line we have a new array which is created and which has the size of n. So we know that this is O of n space. Next, we have this integer I, and that's it. Inside the for loop we have just some array access. So what is the highest term here? We have a lot of constant space complexities, but here we have one O of n and one O of n times m complexity. And we know that this is a higher term, so the total space complexity is O of n times m for our algorithm. So as you can see, it is very similar to calculating the time complexity. Just when we are calculating the time complexity, we cared about the for loops, the while loops, the nested loops, which gave the highest term. But here we are caring about the arrays, matrices, or data structures that use a lot of space. To recap how to determine the total space complexity of some algorithm, so we can just look for every new variable that we declare and determine the total space complexity for this individual part. And then when we have these separate parts, we just look what part does have the highest term in it. So here we saw that it's n times m. In the first example, every part has O of 1, and in the second example we have two variables with O of n space, so the total is O of n. So just solve each part individually and take the highest term. So that's it, guys. I hope you find this really easy. For me personally, it is much easier than calculating the time complexity, because we don't have any weird calculations like in the previous examples where we got these logarithms or similar things, or calculating some formulas or similar things. So we just look at every variable and determine the total space for this part and take the highest of them all. So that's it, guys. Thank you for your attention. And next, you will be challenged with some quizzes where you can get hands-on with time and space complexity. Thank you, guys, and good luck. Hi, guys, and welcome to the sorting section. Let me first explain you what is the problem that we are going to focus on in this section. Let's say that we are given a sequence of numbers and our task is to order them from the smallest to the largest number. In other words, we have to sort the sequence or array in non-decreasing order. Sorting is one of the most common algorithms in the world. If you look around, you can find a lot of applications that are using a sorting algorithm to put elements of some list in certain order. The elements don't have to be numbers, they can be strings or maybe some events which are sorted by date. In the next videos, we will learn several sorting algorithms. So first, we are going to learn 3 quadratic algorithms which are called bubble sort, selection sort and insertion sort. These 3 algorithms are not so efficient, but they are must-know algorithms in the world of sorting. After that, we will go on to more efficient algorithms like merge sort and quick sort. And finally, we are going to look at counting sort, which can be really efficient when the data satisfies some constraints. At the end of this section, you will learn the most important sorting algorithms and you will be able to determine what is the best algorithm to use depending on the type and range of the data which needs to be sorted. For each of these algorithms, we will determine the time and space complexity and compare their trade-offs. So let's begin, guys, and happy learning. Hi guys, let's learn about bubble sort. So bubble sort will be the first sorting algorithm that we will learn in this section. So bubble sort is pretty easy and quite intuitive, as you will see. And probably if you don't have any idea about algorithms and you get this problem to sort some array, you will end up doing some algorithm that is similar to bubble sort. Okay, so let's see how does bubble sort work. So here are the steps of our algorithms, and we have 3 simple steps. So the first step is traversing the array and comparing 2 adjacent elements. Then, when we compare these 2 adjacent elements, if they are in wrong order, we swap them. So this means if a bigger number is in front of a smaller number, we have to swap them because they are in wrong order if we are sorting in a non-decreasing fashion. And the third step is that we repeat this process while our array is not sorted. So this process, these first 2 steps will be repeated until we get our array sorted. So these are really easy steps, I think. Let's simulate the algorithm on this example array. So as the first step says, we have to traverse the array and compare 2 adjacent elements. So if we compare 7 and 5, we see that they are in the wrong order because 7 is greater than 5, so we have to swap them. Okay, next 2 numbers, 7 and 9, they are in the correct order because 7 is less than 9. Okay, next 2 numbers, 9 and 15, also okay because 9 is less than 15. Next 2 adjacent numbers, 15 and 2, and this pair is in wrong order because 15 is greater than 2, so we have to swap these 2 numbers. 2 goes here and 15 goes here. Next step, we compare 15 and 28 and we see that they are in correct order. Next pair, 28 and 11, and we see that they are in wrong order and we have to swap them. 11 goes here and 28 goes here. And finally the last pair, 28 and 3, we have also to swap these 2. 3 goes here and 28 goes to this place. So we have done one iteration over the whole array. So we repeated these 2 steps, but now here we have to check if our array is sorted. So here we see that our array is not sorted because we have still some remaining elements that are not in the wrong order. So we repeat the process. We make another iteration through the array. the same process repeats. So from the beginning. An interesting fact is that in the first iteration of bubble sort, the biggest element in the array will end up at the last position. So the biggest element is at its correct position, because when we traverse our array from left to right, we move the biggest element towards its right position. So similar thing will hold in the second iteration, where the second largest element will end up at its correct position. So we'll see this next. So let's start the next iteration of bubble sort. 5 compared to 7, these are in correct positions. 7 and 9, they are okay. 9 and 2, they are in wrong order, we have to swap them. 2 goes here and 9 goes here. Okay? Now 9 and 15, they are alright. 15 and 11, they are in the wrong order. 11 should be before 15. So we swap them. 11 and 15 goes here. And here we compare 15 and 3. And as I mentioned earlier, we move the second biggest element towards its right position and we swap these two. 3 and 15. Okay, so now we check whether, and finally we can compare 15 to 28, and we know that these two are in right positions because we have done 2 iterations and the 2 of the biggest elements are in their correct positions. So next iteration, because our array is not already sorted, 5 and 7 are in right order, 7 and 2 are not in right order, so we swap them. 2 goes here and 7 goes here. 7 and 9 are alright, 9 and 11 are also okay, 11 and 3 are not okay. So we have to swap. 3 goes here and 11 goes here. 11 and 15 are okay, and 15 and 28 are okay. And here we have the 3 biggest elements in their right positions. So let's move to the next iteration. So here 5 and 2 are in the wrong order, so we swap them. 5 and 7 are in right order, 7 and 9 are in right order, 9 and 3 are in wrong order, so we have to swap them. 9 and 11 are okay, 11 and 15, and 15 and 28 are okay. So next iteration, the array is almost sorted, but we have to do a bit more job. So next iteration, 2 and 5 are okay, 5 and 7 are okay, 7 and 3 are not okay, so we have to swap them. 3 goes here and 7 goes here. 7 and 9 are okay, and everything else in the array is already sorted. So we will always have some suffix or some ending of the array that is already sorted. Let's go to the next iteration. 2 and 5 are okay, 5 and 3 are not okay, so we swap these two. 5 and 7 are okay, 7 and 9 are okay, 9 and 11 okay, 11 and 15 okay, and 15 and 28 are also okay. And now we look at our whole array and we see that we've got an assorted array. So the algorithm is finished. So we have seen that bubble sort follows these simple steps, and we have simulated the algorithm on this example, and finally we have our array sorted. And in the next video, guys, I'm going to show you how to implement this algorithm in Java. Now let's look how to implement bubble sort in Java. So here we have a class called bubble sort, and let's see what functions do we have in our class. We have several helper functions, like this swap function, which basically takes an integer array and 2 indices in this array and swaps the 2 elements at the indices I and j. Another helper function is this print function, which takes as input an integer array and just prints it out to the console. So let's look at our sort function. Our sort function takes as input an integer array, and we declare that n is equal to the array length. And as we saw in our previous example, we have to repeat the traversing of the array until our array is sorted. So here we have a while loop, which seems to be an infinite while loop. So this condition will always be true. But here we must have some break condition, which we will talk about in a minute. In this while loop, new iteration of traversing the array begins. And at each start of traversing, we set a Boolean variable called swap to false. This means that this Boolean variable tells us whether we have swapped any two elements in the array or not. And if after traversing the array, this variable stays false, this means that there don't exist any two numbers which are in the wrong order. So we didn't do any swaps, so this means that our array is sorted and we can break from the while loop. So let's look at our for loop. I goes from 0 until I is less than n-1, and I increments by 1. This condition is because we always compare two adjacent elements, I and I plus 1. So I has to be less than the index of the last element, because the last element doesn't have a next element in the array. So we have to be careful for index out of bounds here. And at each iteration of the for loop, we check whether these two elements at index I and I plus 1 are in correct or wrong order. If the element at index I plus 1 is less than the element at index I, this means that these two are in wrong order because the smaller one is on the right side and it should be on the left side near the beginning. So we have to swap these two elements. So we use our helper function called swap, and we give it as input the input array and two indices which will be swapped, I and I plus 1. What does the swap function do? It saves array of I in a temporary value, then at the index I in array it puts the value which was on index j, and at index j we put the old value of index I, and this is the one we saved earlier. Because if we didn't save the temporary value here, we would lose the old array of I value. So here we swap these two elements and we mark that we have done one swap. So we found a pair of elements which were in wrong order. And this is it for this for loop. After the for loop ends, we just check if we haven't done any swaps. This means that the array is sorted, so we can break out of the loop, of the while loop, and end our algorithm. And this is really simple, I think. Bubble sort is one of the simplest sorting algorithms. In our main function, we just create a sample array, call the sort function on it, and print the array to the console. So let's just check whether our algorithm works. Let's start the program and let's see the output in the console. As we see, we got a sorted array here from the smallest element to the largest element. Now let's analyze the time and space complexity of our algorithm. So first we can say what is the space complexity of our algorithm. In this section, because we are working with sorting algorithms, we won't be counting this array, this input array in the total space complexity. We are just curious, does the sorting algorithm use any extra space besides these n elements in the input array? So let's see, do we use any extra space here? Here we have one integer, boolean, and one integer, and we see that we don't use any extra space in our algorithm. So the extra space we use is constant, so we denote it as O of 1. And what about the time complexity? So what are we doing? We have a while loop, and inside this while loop we traverse one time through the whole array. So the main question is how many times does this while loop execute in the worst case. So the worst case for bubble sort is that our array is sorted in decreasing order, for example 5, 4, 3, 2, 1. Then after our first iteration it would look something like this. We move the 5 to its position and everything else stays in the same relative order, so it would be 4, 3, 2, 1 and 5. Next we move the 4 in its position, 3, 2, 1, 4, 5. Next we move the 3 in its correct position, 2, 1, 3, 4, 5. And finally we move the 2 in its position and we got a sorted array. So we see that when our array is sorted in decreasing order, we will make exactly n iterations in the while loop, because at each iteration of the while loop we just move one element to its correct position. So in this iteration we just moved 5 to its correct position. In the next iteration we moved the 4 in its position. In the next iteration we moved number 3 in its correct position, and then number 2, and finally number 1. If we have n elements, we have n iterations of the while loop, and inside the while loop we have n iterations of the for loop. So obviously the time complexity of bubble sort is of n squared. That's it, guys, about bubble sort. And now let's look at this table. We will look at this table at the end of the lecture of every new algorithm that we learn, and we will compare them to know which ones are more efficient, which one take less time and more space, or less space and more time, and similar things. So we will come back to this table when we learn new algorithms, and we will try to compare them, which ones are better, which ones are worse, and so on. So that's it, guys, about bubble sort. Now let's move on to the next sorting algorithm. Hello guys, and let's continue our sorting journey. In this video we will talk about another sorting algorithm, which is called selection sort. So here we have a quick explanation how does selection sort function. So we begin by dividing the array in two parts. One sorted subarray which starts empty. This means that the sorted subarray contains no elements at the beginning, and the second part is unsorted subarray which starts full. This means that the unsorted subarray contains each element of the array in the beginning. And in each iteration of selection sort we pick the smallest element from the unsorted subarray and append it to the sorted subarray. So in each iteration we pick the smallest element from the right group and append it to the end of the left group, where the left group is the sorted group and the right group are those elements who are yet to be sorted. Selection sort is very simple, and probably it would come to your mind without knowing this algorithm. But let's simulate this algorithm on our example array. So we said that at the beginning we divide the array in two parts, the sorted and the unsorted group. So we will denote the sorted group with the green marker and with the green pen, and the unsorted group with the red pen. At the beginning each element is in the red group, so this means the red group contains the whole array and the green group is empty. So let's begin the first iteration. In the first iteration we find the smallest element in this red group. The smallest element is this number 3. So what we are going to do is that we will take this 3 out of the unsorted group and append it in the sorted group. So let's do it. So how can we do this? We can divide the array in two parts, a sorted prefix and an unsorted suffix. So when we want to append this, number 3 to the sorted group, we just have to swap it with the first element in the red group and decrease the length of the red group to here. So what we are going to do is to swap the 9 and the 3 and put this element in the green group. So we increase the length of the green group by 1, and here we see that now our sorted group contains some prefix of the array which is sorted, and the unsorted group is a suffix of the array which has to be sorted, which has yet to be sorted. So let's move to the next iteration. We find the smallest element in the unsorted group, which is now smaller by 1 element. So the smallest element here is the number 5. So we will swap the number 5 with number 11 and increase the green group and decrease the red group. So let's do this. So we have swapped 5 and 11, and now we have to increase the green group. Okay, so we have done 2 iterations, and we have the sorted group of length 2, and we have an unsorted group of length 6. Let's move on. In the next iteration, we pick again the smallest element from the red group, and this is the number 6. So we swap number 6 and the first element in the red group, so we can increase the green group to this element. So let's swap 6 and 9. And now we have to increase our green group. Okay, that's it for this iteration. We have a sorted prefix of 3 elements. Let's move on to the next iteration. The smallest element in the red group is the number 9, so we swap it with number 22. And we increase the length of the sorted group. Okay, so now we have half of the array sorted, and we can see that from the example until now, we can see that the length of the sorted group will be equal to the number of iterations we have done. So because in each iteration we pick 1 element from the remaining of the array which is unsorted and append it to the sorted subarray. So let's move on to the next one. The smallest element here is 11, so we swap it with 15, and we append the 11 to the sorted subarray. Okay, we have couple more iterations left. We are almost done. The smallest element here is the element 15, so we swap 15 and 22, and we increase the length of the green subarray. And we have one more iteration where we pick the smaller of these 2 numbers, which is 22, and we swap them. And now we have to increase the length of the sorted subarray. And now we have one more number in the unsorted subarray, but basically we don't have to do anything here because we have only just one number, which will be for sure the smallest in this subarray. So we just append it, and so we don't have to do any swaps. We just have to increase the sorted group to the whole array. Okay, and that's it, guys. We've got ourselves a sorted array. So the selection sort needs n-1 iterations, because we saw that we have to do n-1 iterations because we have to choose n-1 smallest elements from the right group and append them to the left group, and finally we don't have to do the nth iteration because the unsorted group will consist of only 1 element, so it will stay on the same place as it is. And now, guys, let's look how we are going to implement this. Hi guys, now we will look at the implementation of selection sort. So here we have a similar set of functions as in the previous example with bubble sort. We have a class called selection sort, we have our sorting method, and we have two helper functions, the swap function which swaps the two elements at indices I and j in our input array, and we have our print function which just prints our array function formatted to the console, and in main we create a new array, we sort it, and we print it, just to check whether our algorithm is correct. Now let's look at our sorting method. Our sorting method gets an input, the array which needs to be sorted. We denote as n the array length, and we start the iterations of selection sort. So we said that we will make exactly n-1 iterations in the previous video, because the nth element will stay at its place, because in the nth iteration the unsorted group will contain only one element, so it doesn't have to be moved anywhere. I goes from 0 to n-2 because it's less than n-1, and in each iteration we have to find the smallest element in the subarray from index I to the end of the array. So we have to find the smallest element from this index to the right. So we do this just with another loop. Here we have an integer min which will denote the index of the minimum element in the unsorted group. So as default we said that the minimum element is the ith element, and this is basically the first element in the unsorted group. So we traverse the rest of the array from I+1 all the way to the end of the array, and we just check for each index j if this element is less than the current minimum. So this is the case. We found ourselves a new minimum element, and we set the index of the minimum element to the current index, which is j. So when we traverse the whole unsorted group, we know that the variable min holds the index of the minimum element in this group. So we just have to swap the ith element, which is the first element in the unsorted group, and the minimum index, which holds the minimum value in the unsorted group. And by doing this, we basically expand our prefix which is sorted. So by moving the minimum element at index I, we increase our sorted subarray to index I. So now after this line, our array will be sorted from index 0 to index I. And the right group, the unsorted group, contains elements from index I+1 to the end of the array. So that's it basically, and in the next iteration we will increase the index I, and we will find the smallest element in the array from this index onwards, and so on. We will increase one by one the length of the sorted prefix of our array. And that's it basically. This is a pretty straightforward implementation, I think. And that's it basically. This is a straightforward implementation, I think. So let's look at the time and space complexity of this algorithm. So let's look at the time complexity. Here we make n-1 iterations, but n-1 iterations is the same as O of n. And inside this for loop we have another for loop which iterates from I+1 to the end of the array. So this looks like, so the inner for loop will not execute the same number of operations each time. So we saw this example earlier in our time complexity examples, when the inner for loop will execute first exactly n operations, then n-1 operations, then n-2 operations, and so on until it executes just one iterations. And we know that this is just the sum of the first n numbers, so this is equal to n times n+1 and all divided by 2. But here we see that we will get an n squared factor when this multiplies out, so this means that the time complexity of this algorithm is n squared. Regarding the space complexity, we see that we have our input array, which has n elements, but we said earlier that we won't count this into the total space required, because every sorting algorithm will need to store the array, but we are interested whether this algorithm uses some extra space besides the input array. So we can see that we have one integer here, another integer here, integer I, an integer min, which we use to denote the index of the minimum element, and another integer here. We don't see any new array creations or similar things, so this means that we have O of 1 extra space. Hello guys, and welcome to another sorting lecture. In this video we will talk about insertion sort. So what is insertion sort? What is the main idea? The main idea of insertion sort is that we divide the array in two parts, similarly as in selection sort. So we have a sorted prefix which starts empty at the beginning of our algorithm, and an unsorted suffix which starts full. So this means that at the beginning the unsorted group contains the full array, and the sorted group contains no elements. And what do we do with these two parts? In each iteration we pick the first element from the unsorted subarray. So we pick the first element from the unsorted suffix and insert it into the correct position in the sorted subarray. For example, if we have a sorted prefix, which is this green area, and we have an unsorted suffix, which is this red area of the array. So basically we said that in each iteration we take the first element from the unsorted group, which is this element, and we insert it somewhere inside the sorted group. So we insert this element in its correct position in the sorted group. And by inserting this element in the sorted group, we increase the length of the sorted group and decrease the length of the unsorted group. So this is basically what I am talking about. We decrease the length of the sorted group by 1 because we inserted one element into the correct position in this subarray, and we decrease the length of the unsorted group by 1. And here you can see that this is how our algorithm will work. So in each iteration we will increase the sorted area until finally we have all n elements in the sorted area. So as you can see, this is a very simple algorithm, and now let's simulate this process on this array and try to sort this array in ascending order. So I will denote with the black arrow the first element in the unsorted group. So we'll be iterating and moving this pointer to the right, and in each iteration this will point to the first element in the unsorted suffix. And I will denote with this green line the current sorted prefix. But in the beginning our sorted prefix is empty, so we don't have any green lines in the beginning. So let's simulate this algorithm. In our first iteration we have that the first element in the unsorted group contains the whole array, and the first element inside it is this number 8. And we have to insert it into the sorted prefix. But in the first iteration we don't have any elements in the sorted prefix, so this means basically that we don't have to move this element anywhere. It can stay where it is. We just have to say that we increased the length of the sorted prefix like this. So this element is now in the sorted prefix, which has increased the length from 0 to 1. So basically we see that the first element in the array don't have to move anywhere in the first iteration. You will see later in code that we start our iterations from the second element, so from index 1, because basically it is correct to say that the sorted prefix can start just with this first element inside it, because we didn't do any work
in the first iteration we can just say that the sorted prefix starts with just the first element inside it. So let's move on to the next iteration. So we move the pointer. So now we look at the number 4. Our sorted prefix is this, and unsorted suffix is everything from this 4 towards the end of the array. So now we have to insert this 4 inside this sorted array. How are we going to do this? So we are going to repeatedly swap the number 4 with the element to its left until the number 4 ends in its correct position. So until there exists no element on the left, or the element on the left is less than our 4. So let's simulate this. We have number 4 and number 8. We compare them and we see that the number 4 is less than 8. So this means that 4 should be before 8 in the array, in the sorted subarray. So we have to swap 4 and 8. Okay, now our 4 is here, and we look if we have an element to its left. We don't have any elements to its left, so this means that we stop here, and this is the correct position of the number 4 in the sorted subarray. And by inserting the number 4 into the sorted subarray, now we increased the length of our subarray to 2. So now this is our sorted subarray, 4 and 8. And we move the pointer to the right. Okay, so now we look at the number 2. We want to insert the number 2 in this subarray. So we look at the first element on the left, which is the number 8. 2 is less than 8, so we swap them. Alright, 2 is now here. We compare 2 with the number 4. 2 is less than 4, so we have to swap them. 2 is now here, and 2 is at the beginning of the array, so we don't have any element to its left. So we stop here, and this is the correct position in the sorted subarray of the number 2. And we have increased the length of the sorted subarray to 3. And we move now the pointer to the number 6. So the number 6, we compare it with the number 8. 6 is less than 8, so we have to swap them. 6 is now here. We compare 6 and 4, and we see that 6 is greater than 4. So this means that these two are in the correct order, and we stop here, because this is the correct position of the number 6 in the sorted subarray 2, 4, 6, and 8. Great, we have increased the length of the sorted subarray by 1 more, and now the length is 4. And now we move the pointer to the right. So here we have a number 3. We have to insert the number 3 inside this sorted subarray. So we compare 3 and 8. 3 is less than 8, so we swap them. We compare 3 and 6. 3 is less than 6, so we have to swap. Now we compare 3 and 4. 3 is less than 4, so we have to swap them. And now we compare 3 and 2, and we see that 3 is greater than 2, so we stop here because this is the correct position of the number 3. And we increase the length of our sorted subarray to 5. And we move on to the last element in the array. So we have to insert the number 9 inside this subarray of length 5. So we compare 9 and 8, and we see that immediately 9 is greater than 8. So this means that we don't have to swap them, and the 9 can remain at its position, which is also its correct position in the sorted subarray, which is now the whole array, because we once more increase the length by 1, and we see that now our sorted prefix contains the whole array. The length of our sorted prefix is 6, which is also the length of our array, and we have finished our algorithm, and we see that our input array is sorted. So we have the sequence 2, 3, 4, 6, 8, and 9, which is sorted in ascending order. So that's it, guys, about the introduction of insertion sort. We have seen how does the algorithm sort an array, what does it do in each iteration. Basically, to recap, we divide our array in two parts: a sorted prefix and an unsorted suffix, and in each iteration through the array we pick the first element in the unsorted suffix and we insert it inside the sorted prefix. And by doing this we have increased the length of the sorted prefix and decreased the length of the unsorted suffix. That's it, guys. Now let's look at the implementation.
Hi guys, let's look at the implementation of insertion sort. So we have a class called insertion sort, and inside it we have a couple of functions. As in the previous videos, we also have three helper functions: a swap function which swaps two indices in some array, a print function which just prints the input array, and a main function where we create a new array, sort it, and then print it to check whether our algorithm works okay. So now let's look at our sort function. First thing that we can see that this is a really short function and a very simple algorithm. So in the first line we just store the array length in the variable n, and then we start the iterations of insertion sort. We have two nested for loops. We have a for loop which iterates from 1 to the end of the array, and in this for loop we pick an element at index I, and this is the first element in the unsorted group, and we have to repeatedly swap the element at index I to put it in the right position in the left subgroup, which is a sorted prefix. So why don't we start at element 0? At index 0, this is because at the beginning the sorted prefix is empty, so this means when we pick the element 0 we have to insert it into an empty array. So this means that we won't move the 0th element anywhere, because we insert it into the empty array, it just remains at the same position. So the element at index 0 doesn't have an element to the left, and because of that it will stay at the same position. So this is why we can start the iterations from 1 and not from 0. So we pick an element at index I, and we have to repeatedly swap it with the element to its left until the element ends up in the correct position in the sorted prefix. So we start by j equals to I. So j is the index of our element that we want to put in the correct position in this iteration of the outer for loop. So j will be always our current element which we are inserting. And we have two conditions for the for loop. We have that j is greater than 0, and we have that array of j is less than array of j minus 1. So the first condition is just to ensure that we don't jump out of the bounds of the array. So if j is equal to 0, this means that our element is at index 0 and it doesn't have an element to the left, so we don't have to compare anything, we just stop the iterations. And the second condition is to ensure if our element at index j is less than the previous element, than the element on the left. This means that these two are in wrong order and we have to swap them. And this is exactly what we are doing inside the for loop. We just swap the elements at index j at an index j minus 1. So this is it. This is all the logic in insertion sort. We just traverse the array, pick an element, and repeatedly swap it to the elements on the left until it ends up in the correct position. So until our element is greater than or equal to the element on the left, or our element ends up at the 0th index. So our new element is at the beginning of the array. So this is it, pretty simple algorithm and just a couple of lines of code. Now we can just run our algorithm to ensure that our solution is correct. And here we see that we got a sorted array. So we got as input this array, and the output we sort the array and then print it, and the array looks like this. So it is sorted in ascending order. Okay, so let's look at the complexity of our algorithm. We have O of n in this line, because this for loop iterates n minus 1 times, which is O of n, and inside it we have a for loop which in the worst case iterates from I to 0. So this is the classic example that we had in some previous sorting algorithms and in our time complexity section, where in the first case our inner loop will execute one iteration. In the second case it can be two iterations, and in the third iteration of the outer loop the inner loop will execute 3 operations, and so on until finally the number of iterations goes up to n. And we know that this is n times n plus 1 over 2, and we know that here we will get an n squared term, so this means that the time complexity is O of n squared. The space complexity is also very easy. We see that we have our input array, which is O of n of space, but we don't count that in. We just need to know the extra space of our algorithm, and we see that we just have a couple of integers. We don't create any new arrays or similar things, so the space complexity is O of 1, constant space. And now, as I promised, when we learn a couple of new algorithms, we go back to this table to compare the sorting algorithms that we have learned so far and to compare their time and space complexities. So we can see in this table that so far we have learned 3 sorting algorithms, which are bubble sort, selection sort, and insertion sort, and we can see that they have exactly the same time and space complexity. So we see that the time complexity of each of these algorithms is n squared, and the space complexity is constant O of 1. So with this lecture we end the first part of this section, and we have learned some basic sorting algorithms which are not so efficient, but they are basic and foundational sorting algorithms which are considered a must-know in the field of algorithms. So you should be comfortable with these algorithms and their time and space complexity, and also with their implementations. Now we will look at more efficient algorithms. So we will cover 3 more algorithms, which are quicksort, merge sort, and counting sort. So thank you guys, and now let's look at some more efficient sorting algorithms. Hi guys and welcome. In the first part of this section we were talking about 3 basic sorting algorithms: bubble sort, selection sort, and insertion sort. As we saw, all of these algorithms are very easy to understand and very easy to implement in just a couple of lines. And one advantage is also that they don't use any extra space, they don't create any new arrays, so the extra space of those algorithms is constant, so they just need the memory to store the input array, and they don't create any new arrays or similar things. But one big disadvantage of those algorithms is that each one of them has time complexity of n squared. So each of them has quadratic time complexity. So what this means is that in some cases our algorithms may be inefficient. In some cases our algorithms will be really slow. So let's look at some examples. If, for example, our input array has size 10 to the 4th power, which is 10,000, n squared is equal to 10 to the 4th squared, and this is 10 to the 8th power, which is 100 million. And we know that anything below 10 to the 9th power can be executed in time of a couple of seconds, and this is okay. Our algorithm will store the array in maybe 1 or 2 seconds or so. But for example, if the size of our array grows to 1 million, which is 10 to the 6th power, then n squared will be equal to 10 to the 12th power, which is bigger than 10 to the 9th power, which is 1 billion. We told you earlier that computers can execute this many operations in terms of couple of seconds, but as we see, this is much bigger, 10 to the 12th power. So this means that when the input array has 1 million elements, the selection sort, insertion sort, or bubble sort will take too much time to sort this array. So we could wait for hours or for days for these algorithms to finish. So this is really bad, and this is why we have to find more efficient algorithms which have time complexity less than n squared. So we are seeking for algorithms with better time complexity, and merge sort is one of them. And now let's learn how to sort an array more efficiently with merge sort.
Okay guys, so let's look how does merge sort work. So we have these three steps. Let's look at them. First, we divide our array in two halves. Then we recursively sort the two halves. And finally, when we sorted the two halves, we merge them back together. So these three steps can sound a bit confusing when you read it the first time. So let's look at an example to make it clear how does the algorithm work. Okay guys, so here we have an example array of length 8 with the following elements. Let's follow the steps of our algorithms. First, we say that we have to divide our array in two halves. So let's do this. We have the first half, which is the first four numbers, and we write them down in here, 7, 3, 4, and 8. And we have our second half, which are the last four numbers, and we write them down here. Alright, so we have done the first step. We have divided the array in two halves. So the next step is we have to recursively sort the two halves. This is maybe the trickiest step. So what does this mean to recursively sort the halves? So this basically means that we have to repeat our algorithm on these two halves separately. So the same thing that we were doing on the first array, on our input array, we have to recursively call our function on these two arrays. So basically we have to split this array and this array again in two halves. First we will call recursion on this half, and we again have to split this half in two halves. So let's call our function again on this array. And now we have to split this array in two halves. So we have 7 and 3 on one side and 4 and 8 on the other side. What do we do now? Now we do exactly the same thing. We have to split this and split this. So first we call our function on this array and we split it in two halves, 7 and 3. And what do we have here? Here we have two arrays of length 1. And this is a base case. So here we will stop our recursion. We can't split this array, which consists of only the number 7, in two halves because it contains only one number. And the same case is with this number 3. We can't split this in two halves because it contains just the number 3. And this is what we want, because these two arrays of length 1 are already sorted because they just contain the one element. This means that it is sorted. So this means that here we are done with recursion and we go back to our parent, which is the array 7, 3. And in our parent we were stuck at the second step, recursively sort two halves, but now we are back and we have finished the step because we have sorted the two halves, which are 7 and 3, which are two arrays of length 1, and they are sorted. So now for this array we can merge the two halves back together. And how we are going to do this? We have two halves which are sorted and we have to merge them in one big array which consists of those two halves merged together. So this is the core of the algorithm. How are we going to merge the two sorted halves in one big array? Let's say we have two pointers on the current element in each of those two parts. So we have a pointer here on the first element of this array, which is 7, and the first element of this array, which is 3. We know that these two parts are sorted and we are looking at the smallest elements in those two parts. What number do we write here? Because the halves are sorted, we write the smaller of those two elements. We write down the number 3. And we have to move the pointer to the next element, but here we don't have any elements in our array, so we jump out of the bounds, so we erase the pointer. And now what element will we put in the second position? We will put the smaller of the two current elements in the first array and the second array, because our pointer in the second array has jumped out of the bounds of the array. We have to consider just one element, which is this number 7. And also this pointer jumps out of bounds of the first half. And here we see that we have this part sorted. This merge function, which merges two sorted halves in one big array, is the core of the algorithm, and it maybe isn't so clear how does it work from this example, because we have just two halves with length 1, but throughout the algorithm we will see on bigger arrays and it will be clear to you. So let's continue our algorithm. Let's recap. We have divided this array into sorted halves, this and this. Then for this array we have divided it into sorted halves, which is 7 and 3, and for those two were the base case, so we don't have to divide them, we just return to the parent, and we have merged those two halves in one sorted array. So now we have to sort the other half of our array 7, 3, 4 and 8. So this is the part 4, 8. So again we split this in two halves, which is 4 and 8. And we have these two halves sorted because they contain only one element. And again we repeat the merge function. So we have to merge 4 and 8 in one array with length 2, which is already sorted. So again we have two pointers, one in the first array and one in the second array. We compare the two elements at the two which the pointers point to, which is 4 and 8, and we take the smaller. We take the number 4. Number 4 goes here, and we move the pointer of this array, and because the array has length 1, the pointer jumps out of bounds, so we will just erase it. And for the next element here, we will take the smaller of the two elements in the halves, and because we don't have any element, our pointer is pointing in the first array, because it jumped out of the bounds, we just consider this element, which is the number 8, and we write it down. And we also erase our pointer because we move to the next element, and the next element doesn't exist in this array. And we've got this array sorted, which is great. So now we divided this array in two halves, which is this and this, and we recursively sorted these two halves. We now see that we have sorted array 3 and 7 and 4 and 8. So now we have to merge those two halves in this array of length 4. So let's do this. So in each of those two parts we have a pointer pointing to the current smallest element. So we have a pointer on the number 3 and a pointer on the number 4. So what element should we put here? We look at our two pointers. We have 3 here and 4 here, and we pick the smaller one, which is the number 3, and we write here the number 3. And because we have used the number 3 from this array, we have to move the pointer to the right by 1, because we don't have to consider the number 3 anymore, because we have used it. So we move the pointer to the right. Now the next element, we consider two numbers, which are this number 7 and this number 4, and we take the smaller one, which is the 4. And by taking the number 4, we move the pointer in this array to the number 8. Alright guys, now we have two numbers in our array, and we look for the third number. Again, we look at our halves, we check which numbers are the pointers pointing to. So we have the number 7 here and the number 8 here. We take the smaller one, which is the number 7. And we move the pointer to the right. Because now our pointer will jump out of the bounds, I will write it down here to indicate that we have jumped out of the bounds of this array, so we don't have any elements remaining in the first half. We just have to consider the elements in the second half now. And the final number, we look at again at the two pointers. Here we have an 8, and here we don't have any number because we have consumed all the numbers in the first half. So we just look at the number 8 and we write down the number 8. and we move the pointer to the right, and the pointer jumps out of the bounds, and we have successfully merged the two halves in one big array which is sorted. Great, guys. I hope that after this merge of these two halves in one array, I hope that now it is more clear to you how does the merge function work. Let's move on with our algorithm. So now we have this array sorted, but now we have to recursively sort this array. So let's again repeat everything that we did on this side. We will repeat in a similar fashion on the other side. So we have the array 1, 5, 3, 1, and we divide it in two halves. So here we have 1 and 5, and on the other half we have 3 and 1. Again, here we have an array of length 2. We divide it recursively in two halves, which is 1 here and 5 here. Here we have two arrays of length 1, and we don't have to divide them because we can't even divide them because they have just one element inside it. Because they contain just one element, and they are already sorted. So we return back here, and now we have to merge those two sorted halves in one array. So basically we will do the same thing as here. We just compare those two elements, 1 and 5. We take the smaller one here, and then we move the pointer in the first array, and because the length is 1, we don't have any elements remaining. We just look at the number 5 and write the number 5 here. Okay, we have this part sorted. We move on to the next part, which is 3 and 1, and we divide it in two halves, which is 3 here and 1 here. And we have to merge those parts back together. So again, the merge function, we basically because we have just one element in each of the halves, we take the smaller one at the first position, and we move the pointer in this array, and it jumps out of the bounds. So we just need to consider the number 3 for the second element. And we have merged those two successfully in one sorted array. Now we have these two halves sorted, and we have to merge them in this array of length 4. We execute again our merge function. We have two pointers in our two halves, which point at the smallest elements in the beginning. And let's look what goes in the first position here. So we look at the two pointers. We have 1 here and 1 here. And because these two are the same, it doesn't matter what we will take. So for example, let's take this one, and we write down the 1. And because we took the 1 from the first half, we have to move the pointer in the first half by 1 to the right. Okay, so now for the second element, we consider the two numbers, the number 5 here and the number 1 here. Number 1 is less than 5, so we take the number 1. And by taking the number 1 from this array, we move the pointer to the right. Alright, so now we look at the next two elements, which are the number 5 and the number 3. 3 is less than 5, so we take the number 3. And we move the pointer in this array because we took the number 3. Okay, guys, and the final number, we compare 5 in this half and nothing in the second half because we jumped out of the bounds of the array. We have used all two elements, and we don't have anything in this array to compare with the number 5, so we just take the number 5. And we move the pointer to the right by 1, which also jumps out of bounds, and we have our array sorted. And finally, we have this half sorted and this half sorted, and we have to merge them back together in our input array. So we have sorted array of length 4 and another sorted array of length 4, and we have to merge those two sorted arrays in one big array of length 8, which should also be sorted. Okay, let's look at this. First we clear out everything from our array, And we have two pointers in our two halves, which at the beginning point at the two smallest elements in the two halves. So we have one pointer here and another one here. So let's look what number goes in the first position. So we have the number 3 in our first half and the number 1 in our second half. Number 1 is less than 3, so we put here the number 1. 1 goes here, and because we took 1 from this array, we move the pointer to the right. Okay, so the second element, we compare number 3 with number 1. 1 is less than 3, so we take this number 1. 1 goes here, and we move the pointer to number 3. Now the next element, we compare the number 3 and the number 3 in the other half, and those two are the same, and it doesn't matter which one we will pick. Let's say, for example, we pick the one from the first array. So 3 goes here, and we move the pointer from this array to the next. Okay, now we compare 4 and 3. We see that 3 is less, so we take the 3 from this array. 3 goes here, and we move the pointer. Okay guys, the next number, we compare 4 and 5. 4 is less than 5, so we take the number 4. Here we write the number 4, and we have to move the pointer to the number 7. Okay, the next number, we compare 7 and 5. 5 is less than 7, so we take the number 5. 5 goes here, and we move the pointer to the right. And here we see that we have used all the numbers in the second half, and our pointer points to nothing because it jumped out of the bounds of the array. Okay, so the next element, we have number 7 here, and we have nothing here to compare with because we have consumed all the elements in this second half. So we will obviously use the number 7, and we move the pointer. Okay guys, and the last number, we compare number 8 with nothing on the right side because we have used all the numbers, so we can just take the number 8 and we write 8 down, and we have to move the pointer. And that's it guys, we are finished. We have both of our pointers are out of bounds, and this means that we have used every element of our two halves. And if we look at our input array, we see that we have a sorted array, which is great. So our algorithm works, and I hope you understood how does merge sort work. So basically, to recap, we divide our array in two halves, as we saw here and here. Then we recursively sort the two halves. How do we recursively sort the two halves? Basically, we just divide this half in another two halves, and each one of those arrays we divide again in two halves until we finally get at the base case, which is when we have an array of length 1. And when we have an array of length 1, we know that this array is sorted. We don't have to divide it. And when we hit the base case, we just return back. And for this array, we have two halves sorted, and we merge those two halves back together. Similarly, those two halves we merge back together in this array, and when we have these two halves sorted, we merge them back together. And the same story on the other side. When we sort the two halves of this array, we can merge them back together in a sorted array, and the same story for the big array. We sorted the two halves of length 4, and we merge them back together in one big array. So that's it. Let's analyze why is this algorithm efficient. So in each recursion call, we basically divide the array in two halves. So basically the length of this array is n. The length of each array on this level is n half. The length of each array on this level is n divided by 4. And the length of each array on this level is n divided by 8. And we know that the last level will have the length 1. So how to determine how many levels will this recursion have? So basically we have we divide the number n by 2 on each level, and until the number drops down to 1. And as we saw in our time complexity examples, this is just log with base 2 of n. So this is basically we have log n levels, where the log is with the base 2. So because log base 2 of n tells us how many times do we have to divide the number n by 2 until n drops to 1. And this is what we see here. Because on each level we divided the number n by 2, and we have to know after how many levels will our length fall down to 1. This is basically the log of n. We have log n levels, and we have to find out how many operations do we execute on each level. We see that on each level the sum of the lengths of each array is equal to n. Here we have 8 arrays of length 1, which is 8. In this level we have 4 arrays with length 2, and in this level we have 2 arrays with length 4, and on the first level we have 1 array with length 8. So on each level the length of the arrays, the sum of the lengths of the array is n, and we know that on each level we are doing the merge function. And what is the complexity of merge function? The merge function has linear complexity, because as we saw we have 2 pointers. We have, for example, 1 pointer here and 1 pointer here, and in each iteration the pointers just move to the right, so they don't go back at any time. So they just move to the right until both of those pointers jump out of the bound. So in the worst case we will traverse all the arrays, all the elements in the first half and all the elements in the second half. So we know that the merge function has linear time complexity, and we know that on each level we have n elements. So this means that on one level we will execute O of n operations, because we have n elements and merge function works in O of n time. The total time complexity is just the number of operations per level, which is n, because the merge function is linear. We just move the pointers to the right until we examine all the elements in the 2 halves, and times the number of levels. And we saw here that the number of levels is log n. So the total time complexity of merge sort is O of n log n, which is great, which is a great improvement in comparison with the n-squared sorting algorithms. So that's it, guys, in this lecture. In the next lecture we will look how we can implement merge sort in Java. Hi guys, in this video I will show you how to implement merge sort in Java. So let's look at this code. We have a class called merge sort, and inside it we have a couple of functions. So here we have a print function, which is a helper function which just prints the input array, and down here we have a main function. We create a new array in this line, then we call our sort method, which sorts the array, and finally we print our array. So now let's look how does our sort function work. And here is our sort method. We take as input an integer array, and in the first line of our function we create a new auxiliary array which has the same length as our input array, and we will use this array as a helper array throughout our algorithm to store some intermediate data. In the next line we call a function called sort, which takes this arguments as input. And so what is this function that we are calling here? So this function has the same name as our sort function, but this is basically called function overloading, because this one and this function have the same name, but the compiler can know which one is which based on the arguments that are passed to the function, because here this function expects just one array, and this function expects 2 arrays and 2 integers as input. Okay, so in this line we are calling this function. Let's see what do we take as input in our sort method. The first argument is our input array, which we want to sort. The second argument is our auxiliary array, our helper array. And finally, we have two integers, a low and a high, which represent a lower and an upper bound of the range of the array we want to sort. So if you remember from a previous lecture, we said that we have to split the array in two halves and then recursively sort those two halves. So basically we won't split the array in halves and pass those new arrays in the recursion. We will just change the range of our array we want to sort. So we will use these two integers to indicate that we want to sort our array from the index low all the way to the index high, and we don't care for the rest of the array, which doesn't fall in this range. Okay, so this is why here we pass 0 and array length -1. This basically tells us that we want to sort our array, this array, from index 0 to index length -1, which is basically the whole array. Okay, so let's look inside this function. First, we have a check. This is basically our base case that we were talking about. So because this function calls itself, it's a recursion. Here we see that it calls itself. We have to have a base case where we don't continue the recursion. We said that the base case is when the range we are sorting is just one element. So this is basically this condition, because when high is equal to low, our range consists of only one element, and this is the base case, and we have to return here. We don't consider the next steps, because the array of length 1 is already sorted. Okay. In the next line, we just calculate the index in the middle of our current range from low to high. We just sum those two up and divide by 2. And now we have to divide our array in two halves and recursively sort the two halves. So these two lines are responsible for what I've said. So here we recursively call the sort function, and we pass the array, the auxiliary array, which is the same as we got as input, but what is changed is these two numbers, the range. This line we recursively call our sort function on this range. So basically, after this line executes, our array from index low to index mid will be sorted. This is the idea. So this is our left half, our first half, and in the second line we call the same method for our right half. So from mid +1 to high. So our left half contains elements from low to mid, and our right half contains elements from mid +1 to high. And after these two lines, we have our two sorted halves. So basically the elements from low to mid are sorted, and the elements from mid +1 to high are sorted. These are our two sorted halves, and here we want to merge them in one big sorted array, so that when we merge those two halves, we want to get a sorted array from index low to index high. So this is what we want to get, this range to be sorted in our array. And here we call our merge function. So let's see how we are going to do this. We call our merge function, which takes as input our input array, auxiliary array, the low index, the lower bound, the mid index, the middle index, and high, the upper bound of our sorting range. The last thing we have to see in our algorithm is how do we perform the merge. How do we merge these two sorted arrays in this sorted array? So let's look inside our merge function. Here we have a for loop where we just fill out our auxiliary array. So we want to save the state of our array from index low to index j in our auxiliary array. So currently from low to high we have two sorted halves. So indices from low to mid are sorted, and indices from mid +1 to high are sorted. and because later in the algorithm we are going to change some elements of our input array, we want somewhere to save the state at the beginning of our merge function. We don't want our sorted halves to get messed up, so here we save all the elements from low to high in our auxiliary array, so later we can retrieve them. And this is basically why do we need an auxiliary array, because in the later part of our algorithm here we see that we change some indices of our array, and this can cause that some elements are lost and we can't retrieve them. Let's move on. As we saw in our merge sort introduction lecture, we have two pointers, two indices which point to the current smallest element in each half. So index I, integer I, will be equal to low, which is the index of the smallest element in the first group, and j will be equal to mid plus 1, which is the index of the first element in the second group. And here we start our merge algorithm. K iterates from low to high. In each iteration we want to determine what is the element that goes at index k. As we said, we just have to compare the two current smallest elements in both of the halves, so we compare the two elements at index I and j, and we take the smallest one. But we also have to be careful where one of them goes out of bounds. Let's look inside the for loop. So we have if I is greater than mid, this means that I has jumped out of bounds of our first group, because our first half goes from indices low to mid, and I is greater than mid, so basically this means that we can consume all the elements from the first group, and this means that we can just pick from the right group and we take the smallest element, the current smallest element from the right half. So array of k, at the current index of our array, we put the current smallest element in our second group. And so here we have to be careful, because we have tempered some indices of our original array, but luckily we have saved everything in our auxiliary array, so we can take the original elements from our auxiliary array. So array of k is equal to auxiliary of j, which is the smallest element in the right group. And by taking this element at index j, we have to move the j pointer to point to the next smallest element. Okay, let's look at the next if statement. So if this wasn't the case, we look at this if statement, which says if j is greater than high, and this is basically the same thing, but for the second group. Here we check if the pointer for the second group has jumped out of bounds, because the second group goes from mid plus 1 to high. So if j is greater than high, this means that we have used all the elements in the second half, and we are just left with the first group, so we just have to take the smallest element from the first group, which is auxiliary of I, and we move our pointer to the next smallest element in the first group. Okay, and if none of these two conditions are satisfied, this means that both of these indices I and j are inside the borders of our halves. So this means that we have two elements which we are going to compare, and we will take the smaller of these two. So first we check if auxiliary j is less than auxiliary I. So if the smaller of these two elements is in the second half, we take this one and we move the pointer in this array which we picked. So we picked the right half and we took the smallest element in this group and we incremented the pointer. And in the else condition, this means basically that it's the opposite case. So this means that auxiliary of I is less than or equal to the auxiliary of j. So we have to pick from our first group, our left group, and basically we do that by taking the auxiliary of I and incrementing our I pointer to point to the next smallest element. And this is it. This is all the magic. So we have two pointers on that point to the current smallest element in both of the halves, and we just compare. In each iteration we compare the element which the pointers point to, and we take the smaller of these two and we increment the pointer in the array we have chosen. And this is it basically. This is merge sort. Basically we have a base case, we divide our array in two halves and recursively sort the two halves, and we merge back the two halves in a big sorted array. So let's analyze the complexities. As we said earlier, time complexity will be O of n log n, because we have log n levels of the recursion tree, and on each level we execute this function, and we know that the merge function works in linear time, O of n, because in each we just iterate from low to high, and there are no inner for loops or any similar things. Those two pointers I and j are just moving to the right, so they are moving in one direction, and we will examine all the elements from low to high. So this means that merge has linear time. So log n levels, and we have O of n time per level, so the total time complexity will be O of n log n. Regarding the space complexity, we said that in our sorting algorithms we don't count the input array. In the space complexity we are just interested in the amount of extra space we use besides this array, and it is also obvious that we are creating this auxiliary array which has the same length as our input array, so this is the only array we create in our algorithm. Here we don't, in this function we don't create any new arrays, and in the merge function we also don't create any new arrays. So this means that our extra space will be O of n because of this auxiliary array we use. We go back to our famous sorting algorithms comparison table. We have learned a new algorithm called merge sort, and we saw that the time complexity is O of n log n, and this is a huge improvement. We see that all the above algorithms have time complexity of n squared, but here we have time complexity of n log n, and by decreasing the time complexity to n log n, merge sort can sort arrays of length which have millions of elements in just a couple of seconds, where our previous algorithms would need a lot of time to sort millions of elements. So this is a huge improvement. Here, for the extra space column, we see that merge sort is using O of n extra space, and compared to the above algorithms, we see that it uses more space than these three algorithms because each one of them uses constant space. So this is one disadvantage of merge sort. We use O of n extra space because we create our auxiliary array, which has to be the same length of our input array. So in terms of time, we have made a great improvement, but in terms of space we have a slight disadvantage compared to these algorithms because we use O of n extra space. And I want to mention that merge sort is one of the most commonly used algorithms because it has the worst case time complexity of n log n, so it is really efficient. In terms of time complexity, if our array doesn't have any special properties, O of n log n is the best time complexity we can achieve. So that's it, guys, about merge sort. Thank you and see you in the next lecture. Hi guys, let's learn about quicksort. Quicksort is another sorting algorithm that is very widely used. In this video we will try to understand how does quicksort work, and we will simulate the algorithm to sort a sample array. So let's learn how does quicksort work. So as in our previous lectures, we have a couple of steps our algorithm executes. So first we have to pick an array element as a pivot. So later we will explain what exactly does this pivot mean and how do we choose an element for a pivot. Then when we choose a pivot,
we put the pivot element in its correct position. So we place our pivot element in the correct position in the sorted array. So our pivot element will be placed at the correct position it would be placed on if the array was sorted. And then when we place the pivot, we partition the array around the pivot and recursively sort the two parts. So this can be a tricky step to understand at the first look. So let me try to explain you the final step. Let's say we have an array 3, 2, 5, 1 and 4. And we take the number 3 as pivot. So we have to put the pivot element in its correct position, and this means that all the smaller elements will need to be placed before the pivot element, before the number 3. So we have to place all smaller elements on the left side of the number 3. So basically this we could transform this to something similar to this. We place 2 and 1 on the left side, and then our pivot element comes, and then finally the numbers 5 and 4. So here we see that we have placed our pivot element in the correct position in the sorted array. So every smaller element in the array is on the left side of our pivot, and every bigger element is on the right side of the pivot. So these are the first two steps. So we pick a pivot. Here we pick the first element in the array, and we place the pivot in the correct position. And then finally the third step is we have to partition the array around the pivot and recursively sort the two parts. So this partition basically means that after this we have two groups. We divided our array in two groups. So here we have the left group, which contains every smaller element than our pivot element, and we have the right group which contains every bigger element from our pivot element. And basically now we can recursively repeat the same process on these two groups. So now the number 3, the pivot, is in its correct position, and we know that on the left side there are only smaller elements than the number 3, and on the right side there are only bigger elements than the number 3. But these two parts are not necessarily sorted, and we just need to recursively repeat the same process on these two smaller subarrays. So the subarray 2, 1 and subarray 5, 4. So this is what the final step of our algorithm means. This partition is the core of our algorithm. So we pick a pivot, place it in its correct position, and recursively repeat the same process on the two parts, the left part and the right part. And these two parts don't have to necessarily have the same length. In this example, it happens to be that the number 3 its correct position is in the middle of the array, and the two parts are the same, but it could also be the case that one group is smaller than the other, but it doesn't change anything. We just need to recursively call quicksort on both of those two partitions. So this final step is called the partition of our array in two groups, the left group and the right group. And as you can see, this quicksort has a lot of similarities with merge sort, because it is also a divide and conquer algorithm. So this means that it divides the array in smaller parts and then sorts the smaller parts. So it divides the array in two smaller parts, sorts them independently, and then we've got ourselves an unsorted array. After explaining a bit the 3 steps, let's simulate the whole algorithm on a bigger array. Okay guys, so here we have a sample array 1, 8, 3, 9, 4, 5 and 7. So let's try to simulate the whole process on this array and to see whether we can get this array sorted in ascending order. So let's begin, guys. So in each step of the quicksort algorithm, we have to know what range of our array are we trying to sort. So at the beginning, of course, the
our range is the whole array. So I will mark with the 2 pointers, low and high, our range. Low will mark the lower bound of our range, and high will mark the upper bound, higher index of our range. So at the beginning we want to sort the range from low all the way through high. Okay guys, so now we have our range, and we have to execute the 3 steps from our algorithm. The first step is to pick an array element as pivot. So this step can be executed in many different ways. The pivot element can be chosen in couple of ways, and in our example we will always choose the first element as our pivot element. But there are also variations of quicksort where we can choose the last element in the range, or we can consider the first, the last, and the middle element and take the median of those 3 to be the pivot element. But in our case we'll make things simple, and we will choose the first element as the pivot element. So always the first element in the range, so the element at index low, will be the pivot element. Okay, so here I will write that our pivot element is the number 1. So now let's see how we can execute the second step. So we have to put the number 1 in its correct position. So each element that is smaller than 1 needs to be on the left side of the number 1, and each element which is bigger has to be on the right side. So let's begin. Here for this example where the pivot is the number 1, it is trivial because we can see that it is immediately at its correct position, because there is no smaller element than the number 1, and this means that the number 1 should go on the first position at index 0. But I will show you, I want to be consistent, and I want to show you a systematic way how we can put the pivot element in its correct position. So we have to put each smaller element on the left and each bigger element on the right. So let's see how we can do this. We will have 2 pointers. So we have our first pointer that will point to the first available element after the pivot element, so it will basically point to the index low plus 1, which is this number 8. So we have our first pointer, and we have our second pointer, which will point to the last element in the range, which is the index high, which is number 7 in this case. So we have our 2 pointers, and the red pointer, so the left pointer, which we colored in the red color, goes to the right in each iteration by 1, and the green pointer goes to the left in each iteration by 1. Okay guys, so let's see how are we going to move our pointers. So we have our left pointer, which is colored red, and our green pointer, which is colored green. And these 2 pointers will move in turns. So in the first turn, our left pointer will move, and our left pointer will move to the right until it finds an element which is greater than the pivot element. So basically it will immediately stop, so because 8 is bigger than the pivot element 1, and we stop here. Okay? And then our green pointer will move. Our green pointer moves until it finds an element which is smaller than our pivot element. So 7 is bigger than the pivot 1, so this means we have to move the right pointer to the left by 1. So now the green pointer points to number 5. 5 is also bigger than 1, so we also have to move left by 1. Now we point to 4. 4 is bigger than 1, we also have to move to left. 9 is bigger than 1, we also have to move to the left. 3 is bigger than 1, we also have to move to the left. Now both of our pointers are pointing to the same element, the number 8. 8 is also greater than 1, and we move our green pointer to the left. And finally, we've got until our pivot element until the index low, and so this means that we haven't found any element which is smaller than the number 1, because at the point where the two pointers cross each other, this means that we can finish our pointer movements, and we have put the number 1 in its correct position. So in this simple case, we didn't have to move the number 1 anywhere or to swap any of those numbers on the right side, because indeed the correct position of the pivot element 1 is its original position, because each element is greater than 1, so 1 is at the first position. So now we move on with our algorithm. Okay, so now the number 1, it's in its correct position in the sorted array, and I will denote this with this green line under it, so we know that this part of array is already sorted. And so we have executed the second step. We have put the element in the correct position. We have put the pivot element in the correct position, and now we have to execute the third step. So we have to partition the array around the pivot element and recursively sort the two parts. So here we see that we don't have two parts, we just have the right part, because each element is bigger than the number 1, so it doesn't have a left side, so we just have to recursively call quicksort on this array with 1 excluded. So we have to change our range. So now our low index is here and the high index is here. So now our range is this one, from low to high, because now we have to sort this part of array, and this first part of the array is already sorted. So let's repeat all the 3 steps on the index from low to high. So first we have to pick an array element as pivot. So basically, as we said, we will always pick the element and index low, the first element in the range, for pivot. So we have to change our pivot to 8. Now 8 is our pivot element. Now we have to put the pivot element in the correct position. So first we have to draw our 2 pointers. Here is the left pointer on index low plus 1, and the right pointer is at the end on index high. Okay guys, so now let's execute our algorithm and put the number 8 in its correct position. So we said that we moved our 2 pointers in turns, and first we start with the red pointer. We said that we have to move the red pointer to the right until we find an element which is greater than our pivot element. So first the number 3 is smaller than 8, so we move the pointer. We move our pointer to the number 9, then we check 9 is greater than the pivot 8, so this means that the red pointer stops here. So now we have to move the green pointer, the right pointer. So we said that we move the green pointer to the left until we find an element which is smaller than the pivot element. And basically this is immediately the first element, because 7 is smaller than the pivot element, the number 8. So we stop the green pointer. And now this is very important. So we have our red pointer on the number 9, which is greater than 8, and we have our green pointer on the 7, which is less than 8. And basically the pointers are pointing to the elements which are currently in the wrong group. This 9 is bigger than 8, but it is on the left side, and this 7 is smaller than 8 and it is currently in the right group. So basically all we have to do is to swap these two. So let's do this. So 7 goes here and 9 goes here. Okay guys. And now, because our red and green pointers haven't crossed each other, we again start our movement, and now we have the turn is on the red pointer, so we move the red pointer again. So we check. Again, to repeat, we have to find the first element which is greater than 8. So is 7 greater than 8? No, 7 is smaller, so we have to move the red pointer to the right. Okay, now the number 4. 4 is less than 8. So again, 4 should be in the left group because it is smaller than the number 8. So again, we move the red pointer. Now 5. 5 is less than 8. And this is also okay. 5 should be in the left group. And we move the pointer. So now we point to the number 9. 9 is greater than 8, so we can stop here. Okay, so now we have to move the green pointer. So first we check, to repeat, for the green pointer we have to find the first element which is smaller than the number 8. Okay, so 9 is greater than the number 8, so we have to move the pointer. Now our pointer points to 5. 5 is less than 8, and this means that we stop here. Okay, so we have our green pointer to the number 5 and our red pointer to the number 9. So are we going to swap the 9 and 5? No, we are not going to swap them because our two pointers have passed each other. So the green pointer has passed the red pointer and it is now on the left side of the red pointer. So this means that we have successfully splitted this part in two parts. The left part, which contains just the smaller elements than the number 8, and the right part, which contains the bigger elements. And now we just have to move our number 8 to some position. But what position should that be? What is the correct position? Because our green pointer will in the final step our green pointer jumped from the right group to the last element in the left group, which contains elements which are smaller than 8. So this means that if we swap the 5, which the green pointer points to, with the number 8, with the pivot, this means that pivot on the left side of the pivot there are also only smaller elements, and on the right side there are only bigger elements. So let's swap 5 and 8. 5 goes here and the pivot element goes here. Okay guys, so what have we accomplished here? Here we see that we divided our range from low to high in two parts. So we have our pivot element is here, and this part of the array is sorted. And on the left side, from index low to the index of the pivot, we see that here we have only smaller elements than the number 8, and on the right side we have only bigger elements. So this is what we try to accomplish. So we have put the pivot in the element in the correct position, and now we have to partition the array around the pivot and recursively sort the two parts. Okay guys, so now we have to recursively call the same procedure on this part, 5, 3, 7 and 4, and on this part just the number 9. Let us first call our procedure on the left part from 5 to 4. So now our low index is here and our high index is here. And so we repeat, everything is the same. We repeat the process. So we pick the pivot element, which is 5, which is the first element in our range. And we put our two pointers. Our left pointer goes here and our right pointer goes here. Okay, so now we start our iterations. First we move the left pointer until we find an element which is bigger than the pivot. So 3 is smaller than 5, so we move the pointer to the right. Now we look at the number 7. 7 is greater than 5, so we stop here. Okay, so now we move the right pointer. So we have to move the right pointer to the left until we find an element which is smaller than the pivot. So first we check the number 4. 4 is less than 5, so we immediately stop. And here we check, are there still any elements which need to be swapped? So here we see that we have our red pointer on the left and the green pointer on the right, so they didn't step over each other. So this means that these two, 7 and 4, are in the wrong position because our red pointer is the end of the left group, which needs only to contain the elements which are smaller than the pivot, and our right pointer, our green pointer, points to the beginning of the red group, which should contain only elements which are bigger than the pivot. So this means that we have to swap the number 7 and the number 4. So 4 goes here and 7 goes here. Okay, and now we again move the right pointer. So we check 4 is less than 5, and we are looking for a bigger element, so we have to move the pointer. Now 7 is bigger than 5, so we stop the red pointer, and now we move the green pointer. So we are searching for a number that is less than 5. 7 is bigger than 5, so we move the pointer to the left. Here we have a 4 which is less than 5, and we stop here because 4 is less than 5. And now we don't swap the 4 and the 7 because the pointers have crossed each other. And we finish our pointer movement, and the final step is just that we need to swap our pivot with the element the green pointer is pointing to. So again, to repeat, why this? Because in the last iteration our green pointer jumped from the right group to the last element in the left group, which is the number 4, and it stopped there. So this means if we swap 5 and 4, everything will be okay. And let's do this. So 4 goes here and 5 goes here. Alright. So what do we have here, guys? Here we have our number 5, which is in its correct position. Each element on the right is bigger than 5, and each element on the left is smaller than 5. So we have this part of the array sorted, and we have to recursively call our procedure on the left part and on the right part. So we have to sort the array 4, 3 and the array 7. Okay, let us first call our procedure on the array 4, 3. So we have our low pointer here and high pointer here, and our pivot element is the number 4. Okay, let us draw our pointers. Starts from the index low plus 1, which is here, and our green, our right pointer, starts from the index low, which is also here. So our two pointers point to the same element. Let us start our pointer movements. So here our red pointer points to the number 3, and we check 3 is less than 4, so we have to move the pointer because we are looking for a bigger element. And our pointer points to this number. And because our pointer jumped out of bounds, because we are only interested in the range from low to high, and our pointer is here, which is high plus 1, we stop the movement. Okay, so now we move the green pointer. So we check 3 and 4. 3 is less than 4, so this means we stop because we are looking for a smaller element than the pivot element. Okay, and we just here we have to check whether we need to swap the green and red pointers, and we don't need to do any swaps because the pointers have crossed each other. The red pointer is out of bounds and has crossed the green pointer, so this means we end our pointer movement, and we just need to swap our pivot with the element our green pointer is pointing to. So we have to swap the pivot with the right pointer, because the right pointer jumped in the last iteration from the right group to the first element in the left group. So our green pointer, our right pointer, which is colored green, points to the last element in the left group, and the last element in the left group is certainly smaller than the pivot element, so it is safe to swap these two. So we swap 4 and 3. 3 goes here and 4 goes here. Okay, guys, so now we also have this part sorted. This is our pivot element, and we have to recursively call on the left part because we just have the left part, we don't have any right part. And let's do this. So here we will see an interesting thing. So when the left, low and high are on the same element, this means that our range has only one element and we don't have to do any operations. This is basically our base case, because when we have a subarray of length 1, it is already sorted, so we just return. We don't have to execute any of these steps, so we can safely say that this part is also sorted, and we return the recursion to the parent. So basically we return to the function where we picked, where our pivot element was the number 5, and we sorted the left part, which is 3 and 4 now, and now it remains us to sort the right part, which is just the number 7. But here we see that it contains just the one element, and this is a base case, so it is already sorted. So we can just mark this that is sorted. And finally we have to sort the right part of the state of the subarray where our pivot element was the number 8. So when we put the number 8 here as a pivot, we sorted the left part, which is now 3, 4, 5 and 7, which is now 1, 3, 4, 5 and 7, and we remained with the right part, which is just the number 9. And because this is base case, this is already sorted, so now we have our whole array sorted: 1, 3, 4, 5, 7, 8 and 9. And that's it, guys. So we have our array sorted. I hope now it is clear what steps do we need to follow to sort our array with quicksort. So first we pick an array element as pivot. We said that we are always picking the element at index low. So this is the first element in our range. Then we put the element in the correct position. This is the part where we have the two pointers, which are moving one to the right and one to the left, and in each iteration we compare. In each iteration, if the two elements the pointers are pointing to are in wrong order, we swap them. And finally we swap our pivot element with the element the right pointer is pointing to, because the right pointer jumped in the last iteration from the right group to the last element in the first group. And finally, when we have our pivot element in the correct position, we partition the array around the pivot element and recursively sort the two parts. So we have something like this. We have our pivot element here, I will denote it as P, and we have our left part and right part, and we just recursively call the same procedure on the left part and same procedure on the right part. And this is it. This is how quicksort works, guys. In the next lecture, I will show you how to implement this in Java. Thank you, guys, and see you in the next lecture. Hi guys, let's look how to implement quicksort. In the previous lecture, we saw a simulation and saw all the steps required to execute the quicksort algorithm, and now we will try to implement these steps in Java code. Okay, so let's begin, guys. So we have a class called quicksort, and inside it we have several functions. Okay, so similarly as in our previous lectures, we have a couple of helper functions like this swap function, which just swaps two indices in an array, and we have this print function which just prints an array. Okay, and let's look at the main function. In the main function we create a new array, we sort it, and then we print it. So let's look at our sort function. So this is our sort function, which takes as input an integer array. We store the array length inside the integer n, and here is an interesting step. We shuffle the array, and then we call our sort function, which actually does all the necessary steps to sort our array, and it's this sort function. So we have two overloaded sort functions, one that we call from the main function, and we prepare everything, and we call our recursive sort function, which is this one. Okay, but first let us see why did we shuffle the array at the beginning. So let's look at the shuffle function. The shuffle function does what its name says. It just shuffles the array to get a random permutation. So for each index from 1 to array length, we generate a random integer in the interval from 0 through I. So for each, we generate a random integer in this interval, and we just swap the element at index I and the element at index j. So here we swap those two, and this just generates a random permutation. Okay, but why are we generating random permutation? To see why did we do this, we have to first see how does quicksort work. So to see why do we need to shuffle our array first, let us see at an example. If we have this array as input, 1, 2, 3, 4, 5, 6, let's simulate the algorithm. First we pick the number 1 as the pivot, and it is already in the correct position, and we are left with the right part, which is 2, 3, 4, 5, and 6. Then we pick the next pivot element, which is the number 2, and we are left with the right part, which is 3, 4, 5, 6. Okay, so the next pivot element is the number 3, and it is in the correct position, and we are left with the right part, which is 4, 5, 6. Then again pivot element 4, rest of the array 5, 6. And then finally we are only left with number 6. And from this example, it is obvious that in each iteration we just cut off one element from the array and recursively call our function on the rest of the array. And this, as you can see, can cause our algorithm to execute n-squared operations, because in each call of our sort function, our recursive sort function, we just cut off one element and then call the same function on the rest of the array. And n times we call our sort function to repeatedly find the pivot element and put it in the correct position. And we know that putting the pivot element in the correct position is done with the 2 pointers, which is linear time O of n. This means that the total time would be O of n squared. So this is why before we sort array, we want to shuffle it to generate a random permutation, because we want to avoid the worst case of quicksort, which is an array which is already sorted. Because as we saw, if an array is already sorted, we will just cut off one element in each iteration, and we don't want to do this. Okay guys, so this is why we have first to generate a random permutation, which gives us a highly unlikely chance to get a sorted array. So getting a sorted array after this shuffle is highly unlikely, so very low probability. So this is to make a guarantee that our algorithm is fast enough. So let's look at our sort function, which takes as input the array and our range, which indicates which subarray of our array are we sorting. So this is the range from low to high. So first we have a base case. If our range contains only one element, and we said that if our range contains one element, it is already sorted and we can just return it. Okay, so in the next line we call our partition function, which takes as input the array and the range and returns an integer which indicates the position of the pivot element after arranging the array, so that the pivot element at its correct position, and on the left side there are only smaller elements than the pivot, and on the right side there are only bigger elements than the pivot. So in a minute we will look at the partition function, but let's imagine that we know how does it work. So we have at index j we have our pivot, and anything on the left is smaller, anything on the right is bigger. So we just have to recursively call our function on these two parts. So we call our sort function on the range low to j minus 1, this is the left part, and on the right part, which is j plus 1 to high. And this is it basically. So we have a base case, we partition the array, and we position the pivot in the correct position, at the correct index, and recursively sort the two remaining parts. We just need to look
to look at the partition function. How are we going to put our pivot element in the correct position in linear time? Okay guys, and let's finally look at our partition function. Our partition function takes as input the array and two indices low and high, which indicate the range we want to partition. So we want to put our pivot element in the correct position, and each element on the left should be smaller and each element on the right should be bigger. So let's analyze the code. As you saw in the previous video in quicksort introduction, we have two pointers. Our left pointer I, which starts from low plus 1 because we skip our pivot element, and we have a right pointer j, which starts from the end of the range, so from high, and we have our pivot element, which is equal to array of low, so our pivot element always equals to the first element in the range we are going to sort. And let's start the pointer movement. We move our pointers until they cross each other. So this condition I is less than equal to j. And first we move the left pointer, the I pointer. And the condition is while array of I is less than or equal to pivot. So the pointer I is moving through the left group. So the left group should only contain elements which are less than or equal to pivot. So if an element is less than or equal to pivot, it is okay, and we can just increment our pointer and move on to the next element. And if we jumped out of bounds of the range, so if I is greater than high, we need to stop our pointer movement. So we break out of this loop. Okay? And after this while loop, our index pointer I will either point to the first element which is greater than pivot. So this means that this element shouldn't be in the first group, in the left group, or our I pointer will have jumped out of bounds. It will be equal to high plus 1. So these are two cases. And then we move the right pointer to the left side. So on the right side there should only be elements which are bigger or equal to the pivot. So if array of j is bigger, greater than or equal to pivot, it is okay, and we decrement the pointer, so we move to the left. And if j is equal to low, this means that we have to stop because we don't want to move any further to the left. So after this loop, either j will point to the pivot element to low, or j will point to the first element which is less than the pivot element, and this element shouldn't be in the right group, it should be in the left group. So here we have a check. If the two pointers have crossed each other, we can break out of the loop, out of this big while loop. And if the two pointers haven't crossed each other yet, and we know that our I pointer is pointing to the first element which shouldn't be in the left group, and our j pointer points to the first element that shouldn't be in the right group. So we can easily swap these two, because when we swap the elements at index I and at index j, the two elements will be in the correct groups after the swapping. That's everything in this while loop. So we find two elements that are not in the correct groups and we swap them, and then we again move first the left pointer, then the right pointer, and so on until the two pointers cross each other. And after the pointers stop moving, we have two groups, the left group and the right group, and we have to swap to put the pivot element in the correct position. And as we said in the last iteration, the j pointer jumped from the right group to the last element in the first group, in the left group. So this means that j will point to the last element in the left group, and we can just swap the element at index low, which is our pivot, and the element at index j, which is the last element in the left group, and we know for sure that this element is less than or equal to the pivot, so it is safe to move the pivot from index low to index j.
And that's it, guys. Basically, we just return the index j because we have just moved our pivot element to the index j. When we return our partition index, we store it in integer j, and we just store the left part and store the right part, and that's it. To recap about the time complexity, in the worst case scenario for quicksort is an already sorted array, because we saw that in each iteration we just, so in each recursion call we just cut off one element, and this is bad for our algorithm, so the worst case is n squared. But before sorting the array, we do a random shuffle in O of n time, and after doing a random shuffle, it is highly unlikely that our algorithm will execute n squared operations, and it is, in the average case, quicksort has a good running time of which is O of n log n, the same as merge sort. So in most cases, quicksort is very efficient and it is very commonly used. So guys, to go back to our table, we added a new algorithm quicksort, and to see it running time, so here it says O of n log n, but with 2 stars that should be a warning. So this means we said earlier that in the average case, in most cases, if we shuffle our array, quicksort will have a good running time of O of n log n, but in the worst case scenario, when we have a sorted array, we just decrease the length of the array in each recursion call by 1, so this means that we will have n recursion call, and in each call we do the partition, which is also O of n, so this means that in the worst case quicksort is O of n squared. But so why is quicksort so widely used, even if the worst case scenario is O of n squared? This is because, as we see, it doesn't use any extra space, so regarding the space it is better than merge sort, and in most cases it gives a really good running time. It isn't guaranteed to run in O of n log n time as merge sort, so merge sort is better regarding the time because it is guaranteed to run in O of n log n, but in most cases, and if we do the random shuffle at the beginning, we will end up with a good running time for quicksort. So quicksort is another sorting algorithm. It is very commonly used because it has good running time in most cases, and it doesn't use any extra space. Okay guys, so that's it about quicksort. In the next lecture we will learn about counting sort. Hi guys, we have one more sorting algorithm left in this section, and in this video we will learn about counting sort. Counting sort is a bit different algorithm than those we were learning in the previous lectures, and this is because the previous algorithms are considered to be comparison-based algorithms, because each one of them uses comparison, so they compare two elements in the array to determine which one goes first, and counting sort isn't like that because it doesn't use any comparison at all. So we don't do any comparison in counting sort, but then you may ask a question, how do we know the final order of the array? How do we know which element is smaller and which is bigger, and how to put them in ascending or descending order? So in this video and in the next one we are going to find out how does counting sort work. Okay guys, so counting sort follows several steps. The first step is that we have to count how many times each element in the original array appears and store this number in the count array. So for each element in the array, we have to count how many times does it appear and store those number of a repetition in some array that we can call the count array. So for example, count of I will be equal to the number of times that the number I appears in our original array. So this is the first step. So we count the number of occurrences of each number and store it in an array. The next step says that we have to modify the count array
so that it is now a prefix sum array. Simply said, the second step tells us that we have to modify our array so that each element is equal to the sum of all the previous elements and itself. And this is a prefix sum array. A prefix sum array is an array where each element is equal to the sum of the prefix of the array until that element. So basically, after the modification, our count of I will be equal to the following. So we have to add the old version of count of I, and then we have to add all the previous elements in the array. So we have to add count of I minus 1, count of I minus 2, I minus 3, and so on until we go to the count of 0. So basically, each element in the array should be equal to sum of all the previous elements in the array. So after the second step, count of I doesn't tell us the number of times the element I appears in the array, but instead it tells us how many elements are there in the array such that they are smaller than or equal to the number I. And this is because we have summed up the number of times each smaller element appears in the array. Count I minus 1 tells us how many times the number I minus 1 appears. Count of 0 tells us how many times the number 0 appears. Count of 1 would tell us how many times the number 1 appears. So after this modification, for each index I, we know the number of elements that are smaller than or equal than the number I. Okay, guys? And let's move on to the next step. For each element in the original array, we have to find its correct position using the count array and to put it in the output array. So we will have an output array which will store the correct output order, and somehow we have to use the count array so that for each element of our original array we have to find out its correct position in the sorted order. So after the second step and the prefix sum array, this step is very easy, because if we have some element 5 in the original array and we want to find out what is its correct position in the output array, we can just look up what number is at the index 5 in our count array, and this value tells us how many elements are there, such that how many elements x exist in the array such that x is smaller than 5, smaller than or equal to 5. And by knowing the count, the number of this element, we know in which position we will put the 5 in the correct order. Because this tells us the number of smaller than or equal elements, we can put the number 5 on the index count of 5 minus 1. Count of 5 because we want to jump over each smaller element, and minus 1 because we don't want, because count of 5 also counts the number of 5s in the array, and we don't want to jump over the position where the 5 should be, because 5 is not a smaller element than 5, it is an equal element. So this is why the minus 1. If count of 5 is equal to 4, for example, there are 4 elements which are smaller than or equal to 5, and we know for sure that we have at least one 5. So if we have 4 elements, we will put 5 at the index 3. So 0, 1, 2, 3, and 5 goes here, and each of those elements, and we for sure know that each of those elements will be smaller, because count of 5 told us that there are 4 numbers which are less than or equal to 5. And after doing this, after putting one 5 in the correct position, we have to decrement the count of 5, because there could be another
5 in the original array, and we should put the second 5 in this position. So we have to decrement the number of the count of 5 value. And this is it basically. We repeat this process for each element, and we have our output array sorted. And when we have our output array sorted, we just copy back the elements from the output array to the original array, and we are done. We have a sorted original array. So this is a quick recap of the steps. Now I will simulate this algorithm on a real example. Okay guys, so we have an input array which has 9 elements, which are 3, 2, 2, 0, 5, 6, 0, 5 and 4. So we see that the largest element in our array is number 6. So because we want to store the number of occurrences of each element in the count array, our count array has to be big enough to have an index 6, because our biggest element in array is the number 6. This tells us that the count array size will be equal to the biggest element in the input array and plus 1, so that we have this index in our count array. Okay, so let's follow the steps in the algorithm. First, we can initialize the count array with all zeros. And now we can start our algorithm. We have to count for each element how many times does it appear in our original array. So let's begin. Let's iterate through our input array, and when we see a number 3, we want to increment the counter of 3's in the array. It's that simple. Okay, so now we are looking at the number at index 0. It's the 3, and we have to increment count of 3 in our count array. So here we increment from 0 to 1, because now we have 1, 3 in our array. Next we move on to the second number, which is the number 2, and we increment count of 2 to also 1. We move on to the next number, which is also number 2, and we increment count of 2, and it jumps from 1 to 2. So here we have a 2 now. The next number is the number 0. We increment count of 0 by 1. So now the number 0 appears 1 time. The next number is the number 5. We increment count of 5. We have one number 5 in our array until now. Next is the number 6. We increment count of 6. Count of 6 now jumps from 0 to 1. We move on. Next we have another 0. We increment count of 0, and it jumps from 1 to 2. So we have 2 zeros now. The next element is the number 5. We have to add 1 to the count of 5. Count of 5 is now 1, and it will jump to 2. And the final number is the number 4. We increase the count of 4 value by 1, and it jumps from 0 to 1. And we are done with the first step. When we look at our count array, for each element, for each index, the value count of I tells us how many times does this number appear in the original array. So if we look at count of 4, it tells us that we have one number 4 in our original array. It's true, because we only have one 4, but if we look at the number index 0, we have 2 zeros in our array, and we have 1 0 here and 1 0 here. Okay, let's move on to the second step. We modify the count array so that it is now a prefix sum array. And as we said, for each index, we have to sum up all the values before that index, and also the value at the current index we are looking at. So an easy way of creating a prefix sum array from a normal array is that we start from index 1 and add the value, the index just before it, to the left, to the current value. So the value if we start from index 0, we don't have a left value, so it doesn't make sense.
and we can start from the index 1. So if we look at index 1, we have to add the count value at the previous index, which is the number 2. We have to add 2 to this 0, and this now becomes 2. So here we have a 2 now, and we move on to the next index. For the index 2, we add the previous value, the previous count of I minus 1, which is now 2. So we add 2 and 2, we get 4. And move on to the next index, which is the index 3, which is the index 3. We have 1 here, and on the previous element we have the 4. We add those up, which gives us 5. We have a 5 here. We move on to index 4. We look at the previous element, which is 5, and add up, and we get 6. We have a 6 now here. The next element, we have a 2 here and 6 here, and when we add up, we have 8. And finally, for the index 6, we add up the count of 5 value, which is 8, and here we have a 9. And we are done. So guys, there's a very simple formula. So for when we are calculating count of I, we just need to add the value at the previous element of count, at the previous index of the count array, and we have to increase our current value with the previous value. So we increase count of I by count of I minus 1. And you can imagine like we are moving all the values from left to right, because we carry them from index I minus 1 to index I. And this is how we can create a prefix sum array in linear time. And now after this step, if we look at example at the value count of 4, which is 6, this basically means that there are 6 elements in the array which are less than or equal to the number 4. And if you look at them, these are 1, 2, 3, 4, 5, and 6. So this is now what we've got. If you look at the count of 6 now, it tells us that there are 9 elements which are less than or equal to the number 6, and this is every element in the array basically. Okay, we are ready for the third step. For each element in the original array, we have to find its correct position and put it in the output array. Okay, so we again traverse the input array, and we are going one by one. First we look at the number 3, and we have to find its correct position based on the value in the count array. So we look at the count array, and we see that count of 3 is equal to 5. This means that there are 5 elements less than or equal to the number 3, and we will put the number 3 at index 5 minus 1, which is 4. So the number 3 goes at index 4 in the output array. Okay, and when we do this, we have to remember that we need to decrement the value of the count value of the number that we placed in the output array. This is because if we have another 3, we have to put it on the left position. Okay, let's do this. We decrement the value of count of 3 value from 5 to 4. So here we have a 4 now instead of a 5, because we have used up 1, 3. Okay, let's move on to the next element, which is the number 2. We look at the count of 2 value, which is 4, and we place the number 2 at index 4 minus 1, which is 3. So 2 goes here, and we decrement the count of 2 by 1, and here we have a 3 now. So here we have a 3 now. Let's move on to the next element, another 2, and this is an important step to see. We look again at the count of 2 value, which is now 3, and we have to put number 2 at index 3 minus 1, which is 2, and which is here. And if we didn't increment this counter in the previous step, we would overwrite this number 2, and it wouldn't be a correct algorithm. So it is important to decrement each time we put an element in the original array, and also we have to do this in this step, and count of 2 will drop down to 2. We move on to the next element, which is the number 0. We look at the count array, count of 0 is 2, we place number 0 at index 1. So number 0 goes here, and we decrement the counter of 0 from 2 to 1. The next element is the number 5. We look at the count array, count of 5 is 8, so 5 goes at index 7. We have a 5 here, and we decrement the value from it, and it drops from 8 to 7. The next element in the array is the number 6. We look at count of 6. Count of 6 is 9, so the number 6 goes at index 9 minus 1, which is 8. So number 6 goes here, and we decrement the value of count array of 6 at index 6 from 9 to 8. The next element in the array is another 0. We look at count of 0, which is now 1, and we put another 0 at index 1 minus 1, which is also 0. So 0 goes at index 0. And we decrement the count of 0 value, which is now drops to 0. The next element in the array is the number 5. We look at count of 5, which is now 7, and we put the 5 at index 6. 5 goes here, and we decrement the count of 5 value, which should now be 6. And the final number in our array is the number 4. We look at the value count of 4, which is 6, and we put the 4 at index 6 minus 1, which is 5. 4 goes here, and we decrement the counter. Now here we have a 5. And we are done with the third step of our algorithm, and we can see that in our output array we have a sorted order from the smallest element to the largest element. And this is great, guys. We have one more very easy step left. We just have to copy each element from the output array to the input array, and we are done. So let's do this. So we have a 0 here, 0, 2, 2, 3, 4, 5, another 5, and a 6. And this is it, guys. We finally have our input array sorted. Hi guys, we are continuing our lecture about counting sort, and in this video I will show you how to implement counting sort in Java. So similarly as in previous videos, we have a class called counting sort and several helper methods as our two most important methods, which are this sort function and this counting sort function. Down below we have a helper print function, which just prints the input array, and our main function, which we use to test whether our algorithm works correct and whether it sorts the array in ascending order as we want it to work. So basically we create a new array, call our sort function, and we print our array to check whether everything is fine. And now we are going to look at our sort function. So the sort function takes as input our array, which is an array of integers, and in the first line we store the array length in the variable n. In the next line we create a new variable, which is an integer, and it's called max. This value will hold the current maximum number in the array. So the for loop which follows this line is used to determine the largest number in the array. So we iterate through the whole array from index 0 through all the way to index n minus 1, and for each element in the array we check whether this current element, array of I, is bigger than the maximum number so far. So the new maximum is equal to the bigger of these two numbers, the old maximum and the current element in our array. After this for loop ends, our max variable will hold the largest number in the array. And when we have the largest number in the array, we call our counting sort method, which takes as input our array and the largest element. And let's move on to the counting sort function. So as we said, we have an array and an integer k, which is the largest number in our array. So the first three lines are just the setup. We create a new integer n, which is equal to array length, and we create two auxiliary arrays. We need two helper arrays as described in the previous video. We have an output array, which is the same length as our input array, and we use the output array to store the data in sorted order. While we are traversing the input array, we find the correct position of the element and put it in the output array. And finally, after executing the algorithm, we copy back everything from output array to input array. And we create the count array, which we use to store the number of occurrences of every element of the array. And it, as we said, it needs to have size equal to k plus 1, because we need to have an index which is equal to the highest element in the array. We need to have an index k in our count array, and to have an index k, the array length should be equal to k plus 1, because then the last index in the count array is index k. Okay guys, and now let's move on to the core of the algorithm. So here we have four for loops, which are basically those 4 steps that we described in our previous lecture. So let's start with the first for loop. We iterate through the whole array, and for each element, array of I, we increment count of that value. So count of array of I is incremented by 1. So for each element array of I, we increment count at index array of I by 1. So basically this line tells that okay, the current element is array of I, and note in the count array that we have one more occurrence of this element. So basically this is what this line says. So basically after this for loop, count of some number x will be equal to the number of occurrences of number x. So we know how many times does number x appear in our original array. Okay? The next step in our algorithm is to modify the count array so that now it is a prefix sum array. Basically, now count of I should be equal to the sum of all the previous count of i's, 0, 1, 2, 3, so on until I minus 1 and I. And as we said in the previous lecture, we can do this by this simple formula. We just iterate from index 1 to index k, and in each step we add to count of I the value of count of I minus 1. So the value to the left of the index I. And by doing this, basically we move all the sum of the previous elements from the left to the right. So we move from index 0 to index 1, then in the next iteration from index 1 to index 2, then from index 2 to index 3, and so on. And after this for loop, we made in linear time a prefix sum array. So after this for loop, count of some value x will be equal to the number of elements in original array which are smaller than or equal to x. So after this second step, count of some number x will be equal to this number of elements in the original array which are smaller than or equal to x. And the next step, the third step, we have to traverse our original array, and for each element we have to put it in the correct position in the output array, in the sorted array. And we are doing this by looking at the count value of each element. So we traverse our input array, and in the first line we are determining the correct index in the sorted output array. So the index is equal to count of the current element, array of I, and -1. We said in the previous videos why -1, because this value also counts the elements which are equal to array of I. And if we don't have the -1 here, we could jump over the range where we should put array of I values. So count of array index, new index, will be equal to count of array of I and -1. After determining the correct index in the first line, we put our current element, array of I, in the correct position in the output array. So index is the correct position of our current element in the sorted array. And we have to remember that after doing this, we have to decrement the count value of the current element. Because if we later see another element which is equal to the current element, we don't want to override the element which we put earlier, and we have to put the new element one position to the left, so we don't override anything in our sorted output array. So we determine the correct index in output array, we store actually our current value in the output array in the correct position, and we decrement the count value of the current element. And after this for loop, our output array contains sorted input array, and in the last step we just need to copy each element from output array to input array. So we traverse through the whole array. We have n elements, and for each element, for each index I, array of I is equal to output of I. We just copy over the elements from output to array, where our array is our input array. And after this, our input array is sorted array. And that's it, guys. This is the whole counting sort algorithm. So we have a prep phase where we find the maximum element, and after this we have our counting sort algorithm where we execute the 4 steps that we mentioned that we explained in the previous video and also in this video. And this is it, guys. Let's just analyze the time and space complexity. So here we have one for loop which is of n. So this for loop is of n because we find the maximum element in linear time. Then in the counting sort function we have here another for loop which is also of n. And then let's look at the next for loop. Here we have a for loop which is of k because we have k iterations where k is the maximum element in the array. And the last 2 for loops are also of n because we iterate through our original array which has n elements. And let's see what we've got. So we have of n, of n, of k, of n, and up here of n. So the highest terms are these several of n's, which we can consider just as one of n, and we have this of k, and we don't know which one is the higher term, n or k. So this means that we have to consider both of them, and the total time complexity of our counting sort function is of n plus k. We have n plus k because they are entirely separate. We don't have 2 nested for loops, where one iterates to n and another one to k, but instead we have 2 parallel loops, two entirely separate. See here we have a for loop which iterates to k, and we have several for loops which iterate to n, and because of that we have n plus k and not n times k. Okay, so the time complexity of counting sort depends on the number of elements in the array and the largest number in the array. So this is a new complexity in sorting algorithms. We haven't seen this earlier. The best we had achieved was n log n, but here we see that if k is approximately equal to n, we can write this as O of n, and we have a linear time sorting algorithm. So this can sometimes be written as O of n, but there is a condition that k is approximately equal to n times some constant. If n is around 100,000 and k is also around 100,000 or less, we can say that we have a linear time sorting algorithm, which is really great, guys. But unfortunately, if k is rather huge, let's say 1 billion or 10 to the 12th power, this k factor dominates and we have not so good algorithm. And let's look at the space complexity. So we have our input array, which is O of n space, but we don't consider this, as we said. We just look at extra space, and we know that in these two lines we created new arrays. One is O of n space and another one is O of k space. So the space is also O of n plus k, because we have one array extra array of size n and another one of size k. And let's switch back, guys, to our sorting algorithms comparison table. We learned another algorithm, which is the final algorithm in this section, and it is called counting sort. And we said that the time complexity is O of n plus k, and extra space is also O of n plus k. And we can see that it uses a bit more space than more space than those above algorithms, because it has O of n for the output array and O of k for the count array, because we have to count for each element of the array how many times does it appear. But a potentially great improvement is this time column, where we have O of n plus k time. And as I said, if k is equal to n times some constant, or if k is maybe less than n, then we can say that we have a linear time sorting algorithm. But this condition has to be satisfied, because if k is huge, our algorithm can't even work, because first of the time, if k is equal to the 10 to the 12th power, it will take it will take a lot of time to execute, or it won't even finish. But also the algorithm won't even start, because if k is equal to 10 to the 12th power, we have to create an array as big as 10 to the 12th power, and this is a lot of memory, and it even can't create the count array in the first place, so our algorithm can't even work. So counting sort is a really efficient algorithm if the numbers in the array are in a relatively small range. So if you have elements in the array in the range, let's say for example from 0 to 100,000 or to 1 million or to 5 million or to 10 million, it's okay. And we can say that counting sort is really fast in those situations, even faster than the above algorithms. But when k is huge, we can't use counting sort, because it consumes too much memory in the first place. That's it, guys. In this section we have learned 6 sorting algorithms: bubble sort, selection sort, insertion sort, merge sort, quick sort, and finally counting sort. And I hope you got a good grasp about sorting algorithms, and that now you are confident that you can solve sorting problems, and that you can find the most efficient one the most efficient sorting algorithms for a given problem. So that's it, guys, with the lectures in this section. But before we jump to the next section, you will have an opportunity to test your knowledge in sorting algorithms in a couple of quizzes. So thank you, guys, and good luck. Hi guys, and welcome. In this video we are starting our binary search journey. Binary search is a very important and useful algorithm, and it has a lot of practical applications. And also binary search is one of the most common asked questions in interviews. Interviewers like to ask binary search questions because there are a lot of variations of binary search and little tricks that can be applied to get different behavior of the algorithm and just a slightly different result. So this is a super important topic, and I hope you will get a good knowledge about binary search and you will be able to solve any problem based on this algorithm. So let's begin, guys. Let's see what binary search is. Binary search, as its name says, has something to do with search. So, for example, we have a sequence of objects. It can be any object, but let's say that we have a sequence or an array of integers, like this array. So, we have an array of 9 integers, and, for example, we want to search whether a target value, let's say, for example, 6, whether 6 as our target value appears somewhere in the array. Okay, so this is basic search problem. We have a sequence of objects, we have a target object, and we want to check whether the target object appears in our array. So a naive approach would be to traverse the array one by one. So we check the index 0, here is 1, 1 is not equal to 6, then we check the number 3, 3 is not equal to 6, then the number 4, and then finally we have a match here, 6 is equal to 6, and we can return true, which means that 6 appears in the array, or we can return the index of the number 6, which is the index 3. Based on what we want to have as a result of the algorithm, we can return true or false, or the index of the element in the array. So this approach is called linear search, because we linearly traverse the whole array, one element by one, until we find our object, our element, 6 in this example. But this is not so clever approach, because if we were looking, for example, for number 23, we would traverse the whole array one by one, and we would get to 22 and jump out of the bounds of the array, and we didn't find any matches. So this means that 23 doesn't appear in our array. But we had to traverse the whole array and compare 23 with each element, and to finally see that 23 doesn't appear in our array. And if our array is huge, let's say hundreds of thousands or millions of elements, this would be very inefficient. So we can say that the running time of a linear search is O of n, where n is the length of the array. The array contains n elements. So this is the complexity of linear search. This is very inefficient, and as we said, if our array contains a lot of elements and we don't want just check for one number, we want to check for multiple target values, for a lot of target values, whether they appear in the array or not, this would be a very inefficient algorithm. So we want to improve the performance of search, and this is where binary search comes to help. So let's see how binary search improves our search from O of n to a lot better complexity. So let's look, guys, these notes that are written down about binary search, and I want to explain them one by one. Okay, guys, so the first point says that the array has to be sorted. So this is
a precondition for binary search to work. If our array isn't sorted, then binary search will either give the wrong result or it will be stuck in an infinite loop. So this is a precondition, and you have to remember this. This is really important. So for binary search to be used to search a sequence of integers or sequence of any other objects, this sequence or array has to be sorted, like our sample array, which is sorted in ascending order. Okay, so now when this precondition is satisfied, let's move on to describe the core of the algorithm. In each moment, binary search has a range which it is exploring right now. So at the beginning, so we have two pointers or two indices, a lower bound which we denote as low and an upper bound which we denote as high. So we have low pointer and high pointer, and at the beginning low is set to 0, so low is here, and high is set to n-1, where n is the number of elements in the array, so high is set to the highest index. So our search range at the beginning of the algorithm is of course the whole array. Okay guys, and how does binary search work? In each iteration we look at the middle element of the current range. So we have to find the middle element, which is mid, and we can calculate it like this: low plus high divided by 2. So in our example, low is 0, high is 8, 0 plus 8 is 8, divided by 2 is 4. So mid is here. Mid is at the index 4 in the first iteration. And these two final steps are the essence of the algorithm. So we have to define the target value we are looking for. Let's say, for example, that the target value is the number 4. We are looking for number 4 in our array. Okay guys, so we are in our first iteration. We have low here, high here, and mid here, and we have to follow the last two steps. So basically, when we have the middle element, we compare our target value with the middle value. So here our target is 4 and the middle element is 7. And we can see that 4 is less than 7. So what do we know now? We know that our array is sorted because this is the precondition for binary search, and we know our range is from low to high, and we have a middle element, and we compared 4 to 7, and we saw that 4 is less than 7. Basically, if 7 is greater than 4, then each element on the right side of the number 7, so 8, 11, 15, 22, will also be greater than the number 4, because the array is sorted, and each element on the right side is also greater than or equal than the number 7, because of the sorted order. So this means that we can ignore the whole right side, because if 4 is less than 7, for sure we won't find 4 in the right side, from mid to high. And we know that we can just look at the left side. So the left side is the only potential range that we can find our target for. So this is what this step says. If target is bigger, we look to the right. But this is not the case with this iteration, because 4 is less than 7. But this is the case. If target is smaller, look to the left. So our target is smaller, so we have to move the range to the left and just look at the left part of our range. So we can now move our high pointer on to this element, because everything from here to the right side is bigger than our target element, and we can easily ignore this. So let's move our high pointer. Okay guys, so now when we moved our pointer, we are going to the next iteration and we repeat the same process. So low is 0, high is 3, and we are looking in this range from 0 to 3 whether the number 4 exists. So let's calculate the mid element. Mid is equal 0 to 0 plus 3, which is 3, and divided by 3 divided by 2 is 1, because this is integer division, and mid is now located at index 1. Okay guys, so we again compare target with middle element, and we can see now that 4 is greater than 3. And this means that we can easily ignore everything from this point, from this index to the left, because 4 is greater than 3, and it will be also greater than anything on the left, because 3 is also greater than or equal than anything on the left, because the array is sorted. So we now have to move our low pointer, and we move the low pointer to the index mid plus 1. So basically we move the low pointer here. Let's do this. So low is now here and high is now here. We have cut the range down to 2 elements. So now again we calculate the mid, which is 2 plus 3, 5, divided by 2 is 2, again integer division. So mid is at the same index as low. Mid is also at the index 2. Then we compare 4 with the middle element, which is also of 4. What is this now? 4 is not bigger than 4. 4 is not smaller than 4. Because 4 is equal to 4, we have a match. And we can return true if we want to just check whether 4 appears in the array or not. Or we can return mid, which is the index of the current middle element where we have found the match. So we can return the number 2, which is the index of the number 4 we have found in our array. We compare the target value with the current mid value. If these two are a match, we can return a successful search result from our algorithm, and we are done. Okay guys, so this is the whole logic behind binary search. We use the fact that the array is sorted, and we look at in each moment we maintain the range, the current range we are exploring, and we look at the middle element of the range, and basically if this is our range, we look at the middle element and we check whether we continue the search in the right side or we continue the search in the left side, because the target value is either in the right side or either in the left side. So in each iteration we divide the range by 2. So in each iteration the range is 2 times smaller than in the previous iteration. So here we saw how does a successful search look like. Now we will look at another example where we are looking for a number that doesn't exist in our array, so we can see how does an unsuccessful search terminate with binary search. So guys, let's simulate the algorithm one more time, and now let's look for the target value of 9. So we initialize our variables at the beginning, so low is at the index 0 and high is at the last index, which is 8, and we start our algorithm. So we look at the middle element, which is 0 plus 8 divided by 2, which is 4. So mid is now at the index 4. Okay, and we compare our target value with the middle element. So 9 is greater than 7, so we have to look to the right, where the bigger numbers than the number 7 are located, because 9 is also bigger than 7. So we move our low pointer here. Then guys, we have a range from 5 to 8, and we find the mid of this range, which is equal to 5 plus 8 is 13, divided by 2, and with integer division this is 6. So mid is now here, at index 6. Again we compare 9 with the middle element, which is 11, and 9 is now less than 11. So we have to look to the left side. We have to move the high pointer one to the left of the middle pointer. So high will be now here, and we move on to the next iteration. Now guys, our range is only one element. Our range goes from 5 to 5. The middle element is also 5 because 5 plus 5 is 10 divided by 2, which is 5. So mid is also here. And we compare 9 with 8, and we see that 9 is greater than 8. So we have to move the low pointer to the right. One place to the right from the mid pointer. So low pointer will go here. And we move on to the next iteration. And guys, this is a moment that we can stop our search because our low pointer has crossed the high pointer, and now we have an invalid range because the range goes from 6 to 5, which is invalid because the low pointer should be always on the left side or at the same position as the high pointer. So when this condition is not satisfied, we can easily terminate the search because we have an invalid range. And when we have an invalid range, we can return false from our algorithm. This means that the number 9 doesn't exist in the array, or we can return -1 to indicate, if we want to return the index of the appearance, we can return -1 to indicate that this is an invalid index and the number 9 doesn't appear in the array. So guys, this is how binary search works. It is a clever algorithm, but a simple algorithm, as you can see. It's not so complicated, it just uses the fact that the array is sorted, and you can divide the range by 2 in each iteration. So we are constantly decreasing the search range. But let's analyze the time complexity of binary search. So binary search starts with the range of length n, and after the first iteration. So guys, let's analyze the time complexity of binary search. So binary search will run until the range drops to 0, because in each iteration, when we have a valid range, search range, the binary search algorithm will continue, and the first time our pointers cross each other, then the algorithm terminates. So we know that we start from the range length n, and in each iteration we decrease the range by half. So in each iteration we divide again the range, and after the first iteration we look at the range n divided by 2, and then n divided by 4, and then n divided by 8, and so on until our range drops down to 0 or less, until our range drops below 1, because 1 is the smallest valid range. When our range drops below 1, and then we can for sure terminate the algorithm. So how many iterations will we execute in the worst case? So we have seen this in the previous videos, and we know that when we divide some number by 2, and we want to know when we go down to 1 or below 1, this is basically the log 2 of n. So the time complexity, we can denote T of n of binary search, depending on the number of elements of the array n, is equal to O of log n. Because in each iteration we divide our range size by 2, because we ignore one part and we are exploring just the other part. So we go either left or right. So guys, this is a really big improvement, because log of n is not so big. So let's see an example. If we have n is equal 10 to the 5th power, so this is 100,000, log of n will be approximately equal around 20. And so when we search in an array of length 100,000, we will execute just around 20 operations just around 20 iterations, which is crazy small. But if we search with a linear search, we will execute the whole 100,000 iterations, because we have to compare the target value with each element in the array. So this is a really huge improvement, guys. Even if the array size jumps to even higher, for example, n is equal to 10 to the 9th power, log of n is just 30. So a huge range of 10 to the 9th elements, we can search for a target value in this range and find the value or determine that the target value doesn't exist in just around 30 iterations. And in each iterations we just do one compare. We compare our target value with the mid element. So this is really efficient, guys, and this is the beauty of binary search. It is an easy algorithm, but a very efficient one that solves a very important problem. Because searching for a target value in a sequence of objects is a very common problem. It is a very common problem in today's world. So that's it, guys, about binary search in this video. We are continuing our journey in the next video, where we are going to look at the implementation of this in Java. Thank you, guys, and see you in the next video. Hi guys, we are continuing our binary search journey, and now let's look at the implementation. So as we saw in the previous video, binary search is a very fundamental algorithm. It is a very clever and efficient one, but also it isn't too hard at all. It is actually a simple algorithm. So in this video we will see that its implementation is also simple. As you can see, it has a small code length. This is below 15-20 lines of code. But there are a couple of cases and a couple of lines that you should pay attention to, because a common mistake when implementing binary search is that the search gets stuck in an infinite loop. Because when a range drops to length of 2 or length of 1, a lot of implementations, when they are not implemented the right way, are stuck in an infinite loop, because maybe the pointers don't move, the low pointer stacks or the high pointer stacks, and the algorithm doesn't finish at all. So I want to emphasize those situations, and I want to show you how to implement binary search the right way, so that you can search for any element in any array. So let's look, guys, at this code and explain it line by line. So we have a main function which we use to test our algorithm. We create a new array, and I want to emphasize that the array has to be sorted. In this example we can see that we have an array sorted in ascending order, because if the array isn't sorted, binary search will output the wrong result, or it will stuck in an infinite loop. So in the second line, when we create an array, we call our search function, which is implemented with binary search, and we pass to it our array and our target value. And as I've implemented binary search in this video, so that it returns to us the index of our target value in our array. And if the target value isn't present in the array, we return -1. We will see that later. And when we get the index from our binary search function, we just print the index to the console, so that we can check whether our algorithm works correct. And let's see, guys, our search function. So as we said, we have an input array, and we have a target value as parameters, and we first initialize our pointers. As we said, our starting range has to cover the whole array, so the low pointer is at the beginning of the array, at the first index, which is index 0, and the high pointer is at the last index, which is array length -1. This is the last index in the array. And we start our iterations here in this line. So we start a while loop, which has the condition low is less than equal to high. So while we have a valid range, while the pointers haven't crossed each other, we continue our iterations. So while we have a range of length 1 or more, we are continuing our while loop.
And let's look, guys, what are we executing in each iteration. So in the first line, we have to calculate the index of the middle element in the current range. And as we saw in the previous video, the middle element can be calculated as the sum of the low pointer and high pointer and divided by 2. And this is integer division because both of those are integers. So when we calculate the index of the middle element, we want to compare the target value with the middle value. So in this line we check whether target is greater than the middle element, which is array of mid, where mid is the index of the middle element. And if our target value is bigger, then we have to look to the right side. So this means we have to increase the low pointer to point to the index mid plus 1, which is 1 to the right of the mid element. So basically we know that the mid element isn't our target value and anything to the left isn't the target value, so we can move low to mid plus 1 and we can easily even ignore the mid index. The next case is when target is less than the middle element. So this means that we can ignore the mid element and anything to the right of the mid element, and we just need to look to the left side. So we move the upper bound, the high pointer, to mid minus 1, and we ignore anything from mid to n minus 1. And finally, the third case is the else condition. So if target is greater than mid, it will jump here, it will enter here. Else, if target is less than array of mid, it will end up here. And if none of those are the case, this means that we have found a match, because target is equal to the middle element, and we can return the index of the current element which we are comparing with, which is the mid index, because mid is the index of the middle element which we compare to our target value. And this is it basically, guys. Then if we haven't returned from our function, if we haven't found a match, we have decreased the range by entering here or here, and we continue our while loop until we have a valid range. If we exit out of the while loop and we haven't returned from the function, this is an indication that we have an unsuccessful search, because if we had a successful search, we would have terminated from here and the function would immediately return from here and it would jump to the place where we called our function. But if we end up here, if the while loop terminates, this means that we have an invalid range, and this is indicator that we don't have a match. And we can return the index minus 1 because this is an invalid index in any array. So this is an indicator to the program that is calling our function that the target value doesn't appear in the array. Some tricky lines that I want to emphasize are this one. This should be less than or equal, because when low is equal to high, the range length is 1, and this is also a valid range. The next line is that we calculate the mid like this, low plus high divided by 2. And also the tricky lines are the pointer movements. If target is greater than middle element, we move pointer low to mid plus 1. This plus 1 is very important, and also this minus 1 is very important. If we have moved the pointers just to mid, there exists a possibility that our algorithm will be stuck in an infinite loop. So these couple of lines are very important, and there are different binary search variations where we will alter these lines slightly because we want to achieve a different result. But in this binary search implementation, where we want to check whether our target value exists and to return the index of our target value, or minus 1 if it doesn't exist, this is the correct way to do this. So guys, as I mentioned, as we saw in the previous video, this function has time complexity of log n. So
it has logarithmic time in terms of n, where n is the array length. Because this while loop will execute exactly log n, around log n times, and inside the while loop we have just some comparisons which are of 1, constant operations. So let's run our program to check whether our algorithm works. Okay, so first we call our function with the target value 9 and this array, and our function returns -1. This means that 9 doesn't appear in the array, and indeed 9 doesn't appear in our input array. Now let's look for a successful search, for example the number 4. Let's again run the program, and we see that the outcome is 2, so this means that the number 4 appears at index 2. Let's check 0, 1, 2, and indeed 4 is at index 2, and this is 0 indexed because we return the index from our array, which is also 0 indexed. Let's just try another example, for example number 11. The number 11 appears at index 6. Let's just check 0, 1, 2, 3, 4, 5 and 6. Indeed 11 is located in the index 6. And let's just try another unsuccessful search, let's say number 2, which should be between 1 and 3, but we can see that we don't have the number 2 in our array, and it also returns -1. And this is it, guys. In this video, this is a basic implementation of binary search. So in this variation we are searching for a target value to check whether it appears, and we want to get as a result the index of our target value in our input array, or -1 if we don't have a match. If we want just to check whether the target value exists or not, so if we want to get true or false as result, we just need to change 2 lines. Here, when we are returning the mid index, where we have found the match, we can just return true, and down here when we are returning -1, we can return false, an indicator that we don't have a match in our array. So that's it, guys, in this video. In the next videos we will look at some variations of binary search. Hi guys, in the previous videos we were learning about the basic idea about binary search, and also how to implement binary search for the most basic use case of binary search. So for the case where we want to check for a target value and an array, we want to see whether the target value appears in the array. So our function could return true or false, or we want to get the index at which our target value appears in the array. So this is the most basic use case of binary search. And now in the next part of this section we are going to talk about some variations of binary search. Let's run another example on the code from the previous video. So this is the same code from the previous video, where we have an array of integers and a target value, and we return the index of the target value in our input array, or we return -1, which means that the search algorithm didn't find any matches, so this indicates an unsuccessful search. So what happens if we take as input this array, which has duplicate elements? So we have 3 3s now, 2 4s, 4 6s, and 3 7s, and 2 8s, and so on. And here we want to get the index of the target value 3. So what do you think, what index will be the result? So we have a 3 on index 1, 2, and 3. So let's run the program and check. So we can see that the output index is 3. So it found the target value 3 at index 0, 1, 2, and 3. It basically found this last appearance of the number 3. Okay, let's look at
the target value 4 to see what appearance of number 4 will the algorithm catch. Okay, we run the program again and we have index 5, 0, 1, 2, 3, 4 and 5. Okay, and now again for the number 6. We have index 8 as a result. So this is 0, 1, 2, 3, 4, 5, 6, 7 and 8. So it found this 6 which is sort of in the middle. Or we have 2 6s on the left side and 1 6 on the right side. So there isn't actually any pattern for us to convince ourselves what exact appearance of some number will the algorithm return. For example, we saw that here we got the last 3, the last 4, but we've got the third 6, which is not the last 6. We didn't get the last 6, so we got the 6 before the last. Our algorithm still works, so we implemented this algorithm so that it returns the index of our target value, but it doesn't specify which exact occurrence we want to return. So if we have 4 occurrences of the target value 6, we didn't specify that we want the first, the last, or some in the middle occurrence. So it depends on where are our 6s in the array, where is their position in our array, because depending on how the algorithm moves, choosing the left part or the right half, it ends up choosing one of the 6s, but we don't have a guarantee that it will be the first, second, third, or fourth. So this is okay. Our algorithm works still, but so let's just check the number 2, which doesn't appear at all. We should get -1 as the result, and indeed we get -1. So this algorithm works, but it doesn't specify which exact occurrence of the target value we return. It returns some occurrence, so it returns index of some occurrence, or it returns -1 if there are 0 occurrences of that target value in the input array. If we want a bit more control over what exact occurrence does our algorithm choose, we have to slightly change our binary search implementation. So in this video we will talk about finding the first occurrence of the target value. And let's switch over to our second implementation, which always finds the first occurrence of the element in the input array. Okay, so in the main part we have an array, the same array as in previous example, and we call our first occurrence function, and we take as parameters, we proceed as parameters the input array and target value 7 in this example, and we finally print the index which our algorithm found. And this is our implementation. It is basically just a slight variation of our basic binary search algorithm. So let us just convince that when we run this program, it always returns the first appearance. So let's run for the target value 3. And we get as output 1, 0 and 1, which is the first appearance of the number 3. Let's check number 4. Okay, we get index 4, 0, 1, 2, 3, 4. Let's check the number 6. We get 6, 0, 1, 2, 3, 4, 5 and 6, which is also the first 6 in our array. And this is great, guys. Let's just check a number which doesn't appear for, let's say, number 13. And it should return -1, and indeed it returned -1. So our algorithm looks like it works. Okay, so let's focus on the code to see how do we change our binary search implementation so it always returns the first occurrence of the element in our array. Every condition that should be satisfied for the basic binary search should also be satisfied for this, because this is also binary search, but we move the pointers in a slightly different manner, so that we want to push our algorithm so that it to always return the first occurrence of the target value. So our input array has to be sorted. That condition should also be satisfied. Okay, so let's look at our first occurrence function. again we have an input array and target value as input. Okay, again we start the range on the whole array. Low is equal to 0, high is equal to array length minus 1. And this is the first change in implementation. So here we iterate while low is less than high. And in the previous implementation, I can switch here, we have while low is less than or equal to high. So this is the first change. We iterate while the range has length greater than 1. When we finish the while loop, we know that low and high are equal, and this means that the range consists of only one element. Okay, let's look inside the while loop. This line is exactly the same as in the previous example. We just calculate the index of the middle element in the current range, low plus high divided by 2. And we also have this if statements. These conditions are slightly different than in the previous example. So we can see that now we have an if and else statement, and in the previous we had if, else if, and else. So let's see what do we got here. Now we compare our target value with the middle element. So here we compare if target is greater than the middle element. So if our target value is bigger than the middle element, then we should for sure look only at the right half. And we can also ignore the middle element, because target is bigger than the middle element, and they can be equal because target is bigger. So we can ignore the middle element and everything on the left side. So here we just search the right half. So from index mid plus 1 to index high. The next range will be equal to this because we set low to mid plus 1. So if we enter the else condition, this means that the target value is less than or equal to the middle element. So target could be less, but target could also be equal to the middle element, and we don't know this. And because we know that we have to look on the left side, because we want to look for smaller numbers, but maybe it would also be the case that the target value is equal to the middle element, and so we have to include the mid index in our range. And now we search left half plus middle element. We have to include the middle element because it is a potential candidate for the result, because when we enter the else statement, target is less than or equal to middle element. So the range here is from low to mid. Low will stay the same and high will be equal to the middle element. Okay, the difference between this implementation and the one before is that we have here explicitly asked if target is less than the middle element, but here we are doing these two cases together in one else statement. So here we have the target is less than or equal to mid. Look at the pointer movement like this. So if target is greater, it is for sure not equal to the middle element, and the only thing that we can do is look at the right half. So we ignore the mid element and everything to the left. But if target is less than or equal, it could be equal, so we have to accept and the middle element, we must include it in our search range, but we also want to look for occurrences that are more closer to the beginning of the array. Because we want to find the first occurrence, we want to get closer to the beginning of the array. So you can imagine that we move the right pointer, the high pointer, to the left, so that we have decreased the range. Mid is some candidate for the result, but we also want to search whether there are elements which are a match, but they are even closer to the beginning. So you can imagine like that. And after our while loop ends, we know for sure that low and high are equal. So they are one element. The range consists of only one element, and then we just need to check if the only element in the range, which is array of low or could be also high here because low and high are equal, if this element that we decrease the range to is equal to our target value, then we have found a match and we return its index. Otherwise, if that element isn't a match, this is an unsuccessful search and the target value doesn't appear in our array, so we can return -1. So that's it, guys. We have slightly different implementation. So again, to repeat the differences, here is less than sign, where in the previous implementation we had less than or equal, and here we move the pointers in a different manner. The difference is here, where target is less than or equal to array of mid. In the previous implementation, when the target is equal to the mid element, we immediately returned the index of the middle element. But what are we doing different in our first occurrence implementation is that we don't immediately return. We just say that the range includes the middle element. It is a potential solution, but we also want to look to the left to see whether there are even closer solutions to the beginning. So whether there are solutions with a smaller index. And if there are not solutions with a smaller index, it will in the end return the index that matched in this iteration, but it doesn't matter, our algorithm still works fine. Because we include this candidate, but we also want to look for solutions with even smaller indices. And finally, when we decrease our range to length of 1, we check whether this element is equal to target, and if it is indeed the first occurrence and we return its index. Otherwise, we don't have any solutions. So that's it, guys, about this variation of binary search, where we explored how to implement our binary search algorithm so it always returns the first occurrence of some element. And if our array doesn't contain duplicates, the first and the second implementation will always return the same result. But if the array contains duplicates, this implementation will always return the first occurrence, but the first implementation, for this implementation, so we haven't the guarantee which exact occurrence will it return. It will return some occurrence, but you don't know which one. And with this implementation, we have the guarantee that the first occurrence is returned. So that's it, guys. In this video, in the next video, we will solve a similar problem. We won't again change our binary search implementation so that it always returns the last occurrence of some number. So we have a first occurrence, and in the next video we will explore how to return the last occurrence. Thank you, guys, and see you next video. Hi, guys. As I've said in the previous videos, we are continuing our journey about binary search variations, and in the previous videos we were talking about how to find the first occurrence of the target value, and now we are going to talk about how to find the last occurrence of a target value. So as you can see, this new code and the code in the previous lecture are very similar. They have slight differences, and now we will explore those differences. So here we have the same input array as in the previous lecture. We call our last occurrence function, and it returns the index of the last occurrence of the number 3 in this case, and we print the index. So let us just convince that it always returns the last index. Let's run it a couple of times. So here we have index 3, 0, 1, 2, 3, and this is the last occurrence of the number 3. Let's check for number 4. We get 5, 0, 1, 2, 3, 4, 5. It's also correct. And let's check for number 6. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we also got 9 as a result. Okay, guys, so our algorithm looks like it's working, and it is always returning the last occurrence of the target value. Let's just check for an integer which doesn't appear in the array. Let's say 9, and we get -1 as expected. Okay, guys, that's great. Now let's just explore the differences of this algorithm and the previous algorithm, which always returns the first occurrence. So the first two lines are same in all three implementations. We just set our range to the whole array. this while condition, low is less than high, is also the same as our first occurrence function. So we see that this is the same, and we iterate until we decrease the range length to 1. And the last couple of lines are also the same as in the previous video. So when we decrease the length of our range to 1, we just check whether low is equal to high after this while loop, and we check whether this element that is remaining in our range is equal to the target value. If it is the same, we return its index, and otherwise we return -1 for an unsuccessful search. And let's just look at a couple of lines inside the while loop to explore the differences between our two algorithms. So the first difference, it is a slight difference, but a very important one, is here. The way how we are calculating the middle index. So in the previous lecture, for the first occurrence, we just calculated sum of low plus high divided by 2. But now we are taking low plus high plus 1 divided by 2. So what is the case here? This is a problem where we have a range of even length. So if we have, let's say, 1 and 2 in the range, just two numbers, low is here, high is here. So low is 0, let's say, high is the index 1. Then with the previous implementation, low plus high divided by 2, middle index will always point to the first element. But with this implementation, low plus high plus 1 divided by 2, our middle index will always point to the second element, to the element to the right. Because an even range doesn't have a middle element, we have two elements in the middle, one that is slightly on the left and one that is slightly on the right side. The first occurrence function will always choose the one on the left, and the last occurrence function will always choose the one on the right. And this is how we want our searches to move. If you think about it, it is logical, because we want to find the last occurrence of some number, and we want always to push our algorithm to move to the right. So this is why we're choosing the right middle element. But in the first occurrence, we want always to push the algorithm to go to the left, and this is why we are there choosing the left middle element. And this is a very important, this +1 is very important, because if we don't write here +1, our last occurrence algorithm can get stuck in an infinite loop when it is dealing with an even range. So later I will show you how this problem can appear. Now let's look at the conditions. Here we have a condition if target is less than the middle element. If target is less than the middle element, so we know for sure that we have to move just to the left side. We can ignore the middle element, and we can decrease our range, so that now our range is from low to mid -1, because we decreased high to be equal to mid -1. Mid is for sure not a match, because target is less, so it means we can just look to the left side. Otherwise, target is greater than or equal to the middle element, and this means that the middle element has potential to be a solution, but because we want to find the last occurrence, we want also to look for solutions that are even closer to the end of the array. So for solutions that are more to the right side. And this is why don't we check here whether target is equal to the middle element. We just say that middle is a potential candidate, and we include it in the range, but we also want to look to the right side to check whether there are even better solutions for our last occurrence algorithm, solutions that have higher index. So here the new range is mid to high. These are slightly different. These two are slightly different than in the previous example. You can imagine that for a last occurrence algorithm, imagine the statements like this. For the last occurrence, we always want to move to the right. This is the best case, because we will get the highest index. But in this case, where target is less than the middle element, we we must move to the left. So we don't want to move to the left, we would like to move to the right, but here we must move to the left because target is less than mid and middle isn't a potential candidate, and we have to look for smaller numbers. But when we enter the else, we know that mid is a potential candidate, which may or may not be equal to target, but we include it in the range and we explore whether there are even better solutions for our case, whether there are solutions with higher index. And just to mention, for the first occurrence function, here we would like always to move to the left because we want lower indices, but when target is higher than middle element, then we have no choice, we have to move to the right. Because target is higher than mid isn't a candidate, we want to search for bigger numbers. But if we enter the else, this means the target is less than or equal to middle element, and their middle element is a potential candidate, but we also want to look for lower indices, for better solutions in our case. So this is how I'm thinking when I'm implementing first or last occurrence. This is how I remember how to order the if and else statements. So here we check if target is greater, and in our last occurrence we check if target is less than mid. So you just imagine where would you like your algorithm to go, to the left or the right, but you have first to check whether you are allowed to go. So here we would like to go to the right, but when target is less, we must go to the left side, and we must ignore the mid element. Okay guys, so this is it. This is all the differences. So the differences between the first occurrence and the last occurrence are only inside the while loop. So this is one difference, this +1 in the last occurrence, and these two are a bit different than in the previous implementation. And everything else is the same. So now I just want you to show some problems that could arise in these implementations of binary search. Common problem is that the first or last occurrence algorithm gets stuck in an infinite loop, and the cause of this problem is usually an even range where we don't have the exact middle and we have to choose whether we want the left middle or right middle. So let's look at one such example. So let's change our array so the whole array is just two elements, 1 and 2. And let's say we are searching for 1. Let's run our algorithm. And we get 0, which is correct. Let's search for 2. We should get 1. And we get 1. Okay. And let's change this. So now we calculate the mid exactly the same as in the first occurrence algorithm. So I raise this +1, and it always chooses the first element, the left middle element, as the middle index. So let's run the algorithm again. First for the number 1. And this is what I'm talking about. We are not getting any result. So what is the problem here? The problem here is, just let us check what are low and high. In the first we set low to equal to 0 and high equal to 1 because array length is 2. Okay, so we enter the while loop and we calculate the mid. Mid is low plus high divided by 2. So mid is equal to 1 divided by 2, which is 0 with integer division. And we choose always the left. Of the two middle elements, because the range is even, we always choose the left. With this logic of calculating the middle index. So now we check whether target, which is 1, is less than array of 0, because the middle index is 0, array of 0 is 1. So we see that 1 is not less than 1, because 1 is equal to 1, and we enter the else statement. And there what we say? We say that low is equal to mid. Low is equal to mid, so this means that low doesn't even change. And when we enter the next iteration, low will be equal to 0, high will be equal to 1. Because we set low to mid, low was 0, mid was 0, then in the next iteration low and high will remain also the same. And this is the cause of the infinite loop. Because of this, our algorithm is stuck. And it will never finish because low and high never change. But if I return here the +1, let's run the algorithm again. We get a result which is 0, and because we searched for the number 1, it is correct. So let's see how do we move our pointers in this case. So let's erase this. First we start with low 0, high 1, and let's calculate mid. So mid is equal to low, which is 0, plus high, which is 1, plus 1, and this is 2 divided by 2, and this is 1. So with this algorithm of calculating the mid element, we choose the number 2, the middle element which is closer to the right, because we don't have a perfect middle element. And when we compare the target value, which is 1, to our middle element, which is 2, we see that target is indeed less than the middle element. And we enter this line where we say that high is equal to mid minus 1. So low stays the same, but high will be equal to mid minus 1, where we have 1 minus 1, which is 0. And we go up to check the while loop condition, and we see that 0 is not less than 0, and we have cut down the range to just one element, and we exit the while loop, and here we check whether array of low, which is array of 0, which is 1, whether this is equal to the target value, which is also 1, and we can see that this is a match, and here it returns low index, and low is equal to 0, and this is the correct result. I wanted to emphasize this, guys, because there can be problems with binary search, especially with getting stuck into infinite loops, and this is in most cases because of an even range and not calculating the middle element in the right way. So if we are calculating the last occurrence, we always add the +1, which will round up to the middle element which is closer to the right, closer to high. But in the first occurrence algorithm, we don't have the +1 because we always want to round down to the middle element which is closer to the left side, closer to low index. And that's it, guys, in this video. Each of those variations of binary search has also of log n time complexity because we didn't change the core of the algorithm. The algorithms have some very minor differences, like this condition, or calculating the middle element, or how we are moving our pointers, and so. Thank you, guys, and in the next video we are continuing our binary search variations, and we are solving an important problem. Thank you. Hi guys, and welcome back. In this video we are going to see a very important application of binary search and how we can use these variations that we learned in previous videos to solve an interesting problem in a very efficient way. So let's imagine that we have the following problem. We have an input array which consists of integers which are already sorted in ascending order. And the array could contain duplicates. Like this, we have 3 3s, 2 4s, 4 6s, 3 7s, and so on. And we want to handle queries in a format that we got as query an integer, a target value, and we should be able to answer for some target value. We should be able to answer how many times does this target value appear in the input array. So for each number that the user asks, let's say I ask for number 4, our program should return how many times the number 4 appears in the array. So if we ask for number 4, our program should return 2 because we have 2 4s in this array. If we ask for 6, we should return 4 because we have 4 6s in the array. So linear solution would be that for each time when the user asks number like 4, we iterate through the whole array and we just check if the current number is equal to 4, increase the counter, otherwise just move to the next element. So move to the next element, move to the next element, move to the next element, and here we have a 4, we increase the counter to 1, we have another 4, we increase the counter to 2, and so on to the end of the array. So the linear solution is of n. So for each query we would traverse the whole array. But as I said at the beginning, we can use the variations of binary search to solve this problem in a very efficient way. Okay, so how are we going to solve this? We will use the functions from our previous videos that we learned. I just copied over these functions. We have the first occurrence function and the last occurrence function, which respectively return the index of the first occurrence and the index of the last occurrence. So how are we going to use these two informations? It turns out that everything that we need are just those two informations, because when we have the last occurrence and we have the first occurrence, from these two informations with just a little arithmetic we can find out the total number of occurrences of the target value. So in the main function we create a new array and call our number of occurrences functions, which returns how many times in this input array a number 4 appears in this case. So let's look at the number of occurrences function, because this function is the only new one in this video. So we have an array and a target value. In the first line we call our first occurrence function, where we proceed the same inputs as in our function. We put as parameters the array and the target value, and we get the first occurrence of the target value, the index of the first occurrence. And then again in the second line we call the last occurrence function, and we store the index of the last occurrence of the target value in this variable called last. So when we have those two indices, we need to check whether the target value appears in our array. So if we check whether first is equal to -1. If the first occurrence is -1, this means that also the last occurrence will be -1, and this means that we don't have any occurrences of our target value in our input array, so we can easily return 0. But if we have valid appearance of the target value in the input array, we just need to calculate the result of this statement. So we return last minus first and plus 1. Why returning this? So let's see. So why are we returning exactly this, last minus first plus 1? So let's take an example. If we take the number 3, we have that, let's write this down, we have that the first occurrence will be equal to index 1, because the first 3 is on index 1, 0, 1, and the last occurrence will be equal to index 0, 1, 2, 3. And from these two informations we know that we have a 3 on index 1 and we have a 3 on index 3. But because the array is sorted, each index between 1 and 3 also contains a 3. This is because the array is in sorted order, and we can use this fact that we can just calculate the total number of 3's in our array. So we calculate 3 minus 1, which is 2, and plus 1, which gives us 3, which is the correct answer. If you're wondering why this plus 1, so this is, you can remember this when you have a range from low to high, that there are always high minus low plus 1 elements in this range. So if we have a range, let's say for example from 1 to 5, which are range of integers from 1 to 5, how many numbers do we have in this range? We have 1, 2, 3, 4, 5. So this is 5 minus 1, which is 4, and plus 1, because we also include in the range the first and the last element. So this basically gives us how many elements are in some range, how many elements are in the range from the index first to the index last. And because we can use this formula because the array is sorted, and if we know that there is a target value on the first index and there is also a target value on the last index, and this means that on each index between those two indices there is also a target value. So this is, guys, how we can calculate the total number of occurrences of some target value in our input array. So what is the complexity of this algorithm? The complexity of this algorithm is the following. So what are we doing? For the main we call our function number of occurrences, and here we have one call of the first occurrence function, which is of log n, which is because this is basically binary search. Then we call the last occurrence function, which is also of log n, and here we have just of one operations, which means that these two factors are the highest, and the total time complexity of our function is of log n because we just have two calls of binary search and each of those two calls is log n. So the total time complexity to determine the number of occurrences of the target value in the input array is of log n. And this is a really great improvement in comparison with the linear solution, which is O of n, because when we have an array of millions or even billions of elements, we can determine how many times does any number appear in it in just 20 or 30 iterations or repetitions, which is very, very efficient. The log factor and logarithmic algorithms are very desirable because the log function grows very slowly, because as we said, log n with base 2 of 1 billion is around just 30. So here we see how binary search can be used for problems that are not exactly related to its basic use case. For the basic use case is just checking whether a target value appears in the input array, but there are also very interesting variations and problems where binary search can be used to solve these kind of problems in very efficient way. Okay guys, that's everything in this video. I hope that now you have a good understanding of binary search and how we can slightly alter the binary search implementation and logic to solve some interesting problems. Thank you guys. Hi, in this video we are going to solve an interesting interview problem called unique number. Let's look at the problem statement. We are given an array where each number appears twice, except one number which appears only once. And our task is to find that unique number. So let's look at an example. We are given as input the integer n, which is equal to 7 in this example, and n is equal to the length of our input array. And the second parameter is our input array, and in this example it contains elements 2, 3, 2, 5, 3, 1 and 1. And we can see that each number appears twice, such as we have 2 2s, 2 3s, 2 1s, but only this 5 appears exactly once, and our task is to find this number. So the output for this example is the number 5. Okay guys, so now let's try many different solutions and try to determine which one is the most suitable for this problem. The first solution that we are going to try is a brute force solution. So a brute force solution means that we are going to try each possible combination and that we will pick the one which is indeed the solution. Okay guys, now we are here in the editor and let's implement our first solution. So here I have a simple template, a class called unique number, a main method which we will use to test our solutions, and we will write each solution as a separate method. So the first solution we will write is the brute force solution. So let's comment this out to know how are we going to implement this solution. What is the logic behind it? So the basic idea is that we will try for each number to fix this number and count how many times does this current number appear in the whole array. And after that, basically we just check whether the counter of the current number is equal to 1 or to 2. If it is equal to 1, we have a solution. If it is equal to 2, we have to search for more potential numbers, because this is not the solution. Let's just write it down. Try for each number, check how many times does the current number appear, and if the current counter is equal to 1, we have found the solution. And we know that the current number is the solution. Okay. And after we implement the solution, we have to determine its time complexity and also how much extra space does our solution use. Okay. So let's start with implementation. We will create a public static method which returns an integer because we return the unique number from the array, and we will call it brute force. We take two arguments. We have an integer n, which is equal to the length of the array, and an integer array called array. Okay, so first we have to traverse the whole array and fix the current number. Okay, so let us traverse the array. I goes from 0 to n minus 1, and that is incremented by 1 each time. So that we will create a current number variable which will be equal to array of I. So now we have fixed the current number, and now we have to count how many times does this number appear in the whole array. We will create a counter variable which we will initialize with 0 and increment each time when we find another appearance of the current number in the array. So now we have to again traverse the array and count how many times current number appears. Okay, we will create another for loop which we will denote as j. So we have to traverse again the whole array from 0 to n minus 1, and here we have to check if array of j is equal to current number. We found another match and we have to increment our counter. Okay, and after this for loop, counter will be equal to the number of times the current number appears in the array. So we have to check whether this is a solution. And as we mentioned before, we just need to check the counter variable. If it is equal to 1, we have found the solution and we can easily return our current number. And if this outer for loop exits, this means that we didn't find any number which appears exactly once, and this means that the input array isn't valid, because in the problem statement it said that the input array will contain exactly one element that appears once. So here we will return something like -1 to denote that the array is not valid. And this is the whole implementation. Let's try it out. Let's create an integer array, initialize with some numbers. Okay, so we have two 2s, 2 3s, 2 5s, and the number 1 appears exactly once, so the number 1 should be the solution. And let's call our method int solution is equal to brute force, and the parameters are, we have 1, 2, 3, 4, 5, 6, 7 elements in the array and the input array. Okay, and let's finally print the solution. Okay, let's run it, and we get the output 1. Let's just change something. Let us change that we have 2 1s and only 1 3, and run it again. And now we get 3 as output, and this is correct because we have only 1 3 after this change. Now let's analyze the time and space complexity. So here we see that we traverse the whole array, so we will have n iterations in this for loop, and here we have just some constant operations, and we have a nested for loop. So this loop again traverses the whole array from 0 to n minus 1. So this means that we have n here and n here, which will be equal to the total time complexity of O of n squared, because we have 2 nested for loops, each one iterates to n. Okay, so the total time complexity is O of n squared. Let's look about the extra space. So we won't count the input array because each solution needs to have at least O of n space, because we have our input array as the argument. So we don't want to count this. We want to find out, does our algorithm use any extra space besides this array? And we see we just create some integers, some variables which are constant space. We don't create any new arrays. So this means that the extra space our algorithm uses is O of 1. So this means we have the extra space is constant, just any extra space. A little improvement to our algorithm, which doesn't change the overall time complexity, but it decreases the total number of operations by some little constant, is that here we can check if our counter is greater than 1. So this means that we have found 2 appearances of this number. We can break out of this for loop because we don't have to search any further to the right, because we know that this current number for sure isn't a potential solution because it appears 2 times, because the counter is greater than 1. So this is a slight improvement, but the overall time complexity will stay of n squared. So this is about the brute force solution. It has quadratic time. It doesn't use extra space, which is good, but this quadratic time isn't such a good complexity. We want to lower it down to some better complexity. Because in this case, if our input array would have like 100,000 elements, our algorithm would take a lot of time to execute. We have to think about more efficient solutions, and this is the core idea of coding interview. First, you write a brute force solution, you determine the time and space complexity, and then now is the point where we have to think a little bit and how to optimize our algorithm and how to reduce the time complexity. So let's move on to the next solution. The second solution we will call the counting array solution, because we will use a helper array which we call the counting array, and we will use this array to keep the number of occurrences of each element in the array. So similarly as in counting sort algorithm, we will have a helper array, and for example at index I in the array, the value at index I will tell us how many times does the element I appear in the array so far. Let's move on to the editor to see how we are going to implement this. Okay, so we are writing our second solution, solution number 2, and we called it the counting array solution. Okay, so as we said, we will create a helper counting array which will tell us for each number how many times does it appear. Okay, so count of I, where count is our counting array, will be equal to the number of occurrences of the number I in the input array so far. So count of I will be equal to the number of occurrences of the number I. So we follow the same logic as in counting sort algorithm, which we learned previously in the course. Okay, so here I will write down the placeholder for the time complexity and the placeholder for the extra space complexity, which we will fill in later at the end. Okay guys, so we'll create again a public static int method, which we now call counting array solution, and the same arguments as before, n and integer array called array. Okay, so now let's start our logic. First we have to create our count array. So array of integers count is equal to new int. Now we have to determine the length of our count array, and this is a bit tricky because we don't know the range of the elements in our input array, and we have to check this. So first we have to determine whether our input array is feasible, so we can use the elements in the array as indices in the count array. Because if the array contains an element which is negative, we can't use that as an index in the count array, because the indices are only positive until length -1. So first we have to check this. So we have to find the max number. We will set it to 0. We traverse the array, and each time we check if current number is greater than max number, then max number is equal to that number. And also we can check if array of I is less than 0. We can immediately return -1 because our algorithm can't work when there are negative elements. Okay, so now we know how many elements will there be in our count array. So the biggest number is max number, and the max number will be an index in the count array. So the count array must have length max number +1, because we need to have an index max number in the array. So this means that we need to have one more element. That length must be one more greater than max number. Okay guys, another restriction for this algorithm to work is that the max number has to be a relatively small number, let's say 100,000 or 1 million, but everything beyond that, like 100 million or 1 billion, is too much memory, and we can't even create this array. This is the same restriction as in counting sort algorithm, where the elements must be in a relatively small range. So here we follow the same conditions. Okay, and now guys, after creating our new array, it is initialized with 0 by default in Java. So now we need to iterate through the array and fill the count array. We will iterate through the array, and for each number, so current number is equal to array of I, we will say that count of current number is increased by 1, because this is another occurrence of the current number. After this for loop, we have filled our count array, and we can again loop through our array and check which number has the count value equal to 1. So loop again through the array and find element x such that count of x is equal to 1. Okay, we again loop through the array. So the current number is equal to array of I, and we check if count of current number is equal to 1, then we found a solution. We return current number, and when the for loop ends, if we didn't return anything, again this is an invalid array because no element appears exactly once, and we can return -1. So this is invalid array. If we reach this point, we know that the array is invalid. And this is it about this implementation. Let's analyze the time and space complexity. So here we have a for loop which iterates through the whole array, another for loop which iterates through the whole array, and similar for loop, and each of these three loops have time complexity O of n, so the total time complexity is O of n. So we have a linear time complexity, which is great, much bigger improvement than in the previous brute force algorithm. But let's analyze the extra space. We immediately see that we create a new count array whose length is equal to the max number. So the extra space of this algorithm is equal to O of max number in our input array. And this is bad because, as we said, our algorithm won't even work if some conditions aren't satisfied. So the first condition is that there must not be negative elements. Each element should be positive or greater than, each element should be greater than or equal to 0, because we use those elements as indices in the count array. And another restriction is that the biggest number should be reasonably small, because the memory depends on this value, because we have to create an array which is as big as the maximum number in the array. So those are some restrictions, but we have a much better algorithm in terms of time, but we have an algorithm that won't always work and uses too much memory. So we have made some improvements and some, but we are not satisfied with this space complexity. We have to find something even better. Okay guys, now let's move on to the third solution. Alright, so let's look at the third solution. So in the third solution, we will try to work around those conditions that had to be satisfied in the counting array solution to work, because as we saw, that solution was good, but it used too much space, because its space was equal to the maximum number in the array, and this can be huge. We have maximum number equal to billion or even more. We want to make some improvements. We will keep the same idea, the same basic idea, but we will try to change some things and change some data structures. So we will not use an array, we will use a map, and using a map will help us to overcome those limitations that the previous solution had. So let's look how to solve this problem using a map. And here it is written that this solution is called BST and hashing, because we will use two different implementations of a map implemented as a binary search tree, and a map implemented as a hash map using hashing, because those two implementations will have slightly different complexities, and I want to emphasize these. Okay, let's look at implementation. So guys, we are moving on to our third solution, where we will use a map instead of counting array. So solution 3, map implemented with BST or hashing. Okay, so this implementation will be very similar to our previous implementation. So let us copy everything and just change a little bit. Okay, so we'll copy everything from here and let's just format it. Okay, so here I want just to change that we will create a helper map, counting map, instead of counting array, which will tell us for each number how many times does it appear. Count of I, where count is the map, will be equal to the number of occurrences of the number I in the input array. Okay, alright, so we have to change our method name. Now we will call it counting map, because we use a counting map instead of counting array, and a lot of things are similar as in the previous implementation. Here, this is the part where we checked the conditions for our counting array to work, and we determined the max number. And in this implementation we don't need anything of this, because we want to overcome those limitations of the previous implementation. Okay, so we created a counting array, and now we are going to we will erase this and we will create a counting map. So map, we will create this map. Map is a data structure that works with pairs of keys and values. So each entry in the map has a key, and here we want to specify what is the type of the key, and we will say that this is an integer, and here we have to write the class integer, which is the same as the int data type, but in Java we have also classes for all primitive data types, and you can look at this just like a basic integer. Okay, and the value will also be an integer, because we want to map for some number, which will be the key, to map it to how many times does this number appear in the array. Okay, and we will call the map count. Now we want to instantiate, to create the object, the map object, and here we have two different variations. First, we will use a BST version, which is a tree map. This is basically a map which is implemented with a binary search tree. So binary search tree data structure which allows us for efficient search. So let us instantiate the tree, new tree map. Okay, so here we created our map object, and now let us fill the count map. So we will iterate through, here's a typo, through the array and fill the count array. So we have our current number, and in the previous implementation we incremented count at index current number. And now we'll do something similar. We will say that, so the current number will be a key in our map, and first we need to check whether our map contains this key already. So if count.keys keyset.contains, so if the set of all the keys in the map contains our current number, this means that we want just to retrieve the value for this key and increment it by 1. Because we know that our current number is present in the map, we want to remember what is the previous value of our counter for this element, and here we will create an integer value, previous counter, which is equal to 0. If this is by default, because if this is the first occurrence of current number, the previous counter was 0. But if our map contains the current number as a key, we will say that the previous counter is equal to the value count.get for our key current number. So the previous counter will be equal to the value which was associated with this key. So the previous counter for our number. Okay? After finding out what is our previous counter, we have to increase our counter and update the value in the map. And we will do this as follows. So we will say countMap.put. This method will insert a new pair into the map, and if we are inserting something that a key which already exists, it will just override the previous key, because a map contains just one occurrence for each key. So we can't have two pairs with same keys. So each pair has a different key. So our key is current number, and our new count value is equal to the previous counter and plus 1, because we found one new occurrence of the current number. And this is it. We have filled out our count map. And now in the bottom section, where we are looping through our array and determining what is the count of the element x for each number, we have to change this implementation a little bit. So we have to change this because this is not valid. We have to find out what is the counter value of the current number, and we will do this with count.get, which will get us the value for the key current number. So if the value for the key current number is equal to 1, this means that the current number is the solution, and we can return it. Otherwise, if the for loop finishes and we arrive here, this means that the array is invalid. So to recap, it differs slightly from our previous solution. We had to create a new map which has a key integer and the value is also an integer, and we have implemented the map as a tree map, which is implemented as a binary search tree. So the next difference is that here we had to change a little bit the logic how we are incrementing the counter value for some key. So we retrieve the previous value and we just put a new pair with the current number key and the previous value incremented by 1. So each time we increment the counter of the current key. And finally we just loop through the whole array and check for each number what is the counter of that number. So what is the value in the map for this key, for the current number key. And this is it. So what is the time complexity of this solution? So everything is the same. So a lot of things are similar as before. We have two for loops which iterate to n, but you have to know in the previous solution we had just some array accesses inside the loops, and the array access is O of 1, it is constant, so it doesn't matter. But here we have some map methods. We call method count.put or count.get or count key set contains, and each of these methods for a map which is implemented as a binary search tree has time complexity of log n. So with a map we have no restrictions on the key. The key can be anything, it can be any integer, but when using the array the key can be only, the index can be only just some small, relatively small integer. But with using a map the key can be anything. It doesn't have to even be an integer, it can be a string or some object or anything. This is the advantage of the map. And we know that each call of some map method is of log n, because it uses some variation of binary search to find those values. Because of that it is called binary search tree. And so the overall time complexity is O of n here, and times in each iteration we have an O of log n call for the map. So the total time complexity is O of n log n. Okay, and the extra space is at the beginning we create an empty map, and each time we put a new key in the map. So after this for loop our map will contain at most n pairs, because for each number in the array will be a key. So this means that the complexity is O of n. So we have a slight degradation than in the previous example regarding the time, but n log n is still a really good time complexity. But we have a big improvement in terms of space complexity, because now our algorithm doesn't depend on the range of the input values. So the input array can contain negative integers and also really huge integers, and our algorithm won't crash, it will work. So this is a good improvement. So now I want to show you how by changing only one line in this code we can decrease the time complexity even further. We said that this map is implemented as a binary search tree, and each access, each search and each insert in binary search tree is O of log n. So this is O of log n, this is O of log n, this is O of log n, and also this is O of log n. But by changing the implementation of the map to be a hash map, which is basically a map that uses hashing to achieve even better performance. So hashing is a technique which maps some objects. It can be sequence of objects, it can be some strings or an array of integers or an array of characters like a string, and it maps those objects in just one integer. And what is great about this is that we don't have to change anything in our code. Said just that we changed the implementation of the map, but it is still a map and it uses all the same methods. we say that it has the same interface. So each of the public methods stay the same, and we don't change our code below. And only by changing this one line, because our hash map uses hashing, it has search and insert of 1. So now all of these methods are of 1 and not of log n. So this means that we have now reduced the time complexity to O of n, because we don't have this log n factor anymore. We usually say that this is a constant. So the total time complexity with using a hash map instead of a binary search tree is of n. The space remains the same because it is also a map which has at most n pairs of key values, and this remains the same. We have of n space. So this solution has O of n time and O of n space. So we have made a big improvement in terms of performance, time performance and space performance. But we are not finished. We can do also more improvements. So we can try to decrease the space complexity to O of 1 so that we don't use any extra space. Let's look at more solutions. The fourth solution will be an algorithm which uses sorting. So first we will sort the array, and by sorting the array we will arrange the elements so that the same elements, so the elements which are equal to each other, will be next to each other. So if we have 2 trees, they will be next to each other in the array. If we have 2 4s, they will be also one after other. So we will use this algorithm to determine what number doesn't have a duplicate, and we can do this because we will use the fact that each number which has a duplicate will have the same element on the left side or on the right side. If the current element is different from the previous element and from the next element, this means that this number doesn't have a duplicate. Let's look at the implementation, guys. Okay guys, so we are writing our fourth solution, solution 4. And the fourth solution is based on sorting, because first we have to sort our input array. Okay, so the idea is the following. For example, let's say when we sort this array, we will get an array like this: 1, 1, 2, 2, 3, 5, 5. Okay, and here we see that all the duplicates are brought one to each other, and for each element, so here we have 2 1s, 2 2s, and they are next to each other. And for each number, let's say for 2, if you look at the number to the left, 1 is different than 2, but if you look at the number to the right, here we have another 2. And let's say for this 2, it has a 2 on the left side, for this one it has a 1 on the left side, and this one has a 1 on the right side. But this tree is different from its previous element, which is a 2, and from its next element, which is a 5. So we just need to sort the array and then traverse it, and for each element check if it is different than the element on the left and then the element on the right, and this means that it doesn't have a duplicate, and this is the unique number. So for each element at index I, check array of I minus 1 and array of I plus 1. If none of them is equal to array of I, then this is the solution. Okay, here we will leave the time and space complexity and extra space complexity after we finish our implementation. So we create a public static int method which we will call sorting. We called the solution sorting because the main idea is to sort the array. We have the same arguments, and the first thing we have to do is to sort the array. In Java we can use the built-in sort, which runs in O of n log n time. We saw that we have two algorithms that can run in O of n log n, quick sort and merge sort, and this built-in sort
also works in O of n log n. So we will call arrays.sort and pass our array as the parameter. And after this line, our array is sorted. Now we just need to traverse the array, traverse the whole array, and now we have to check the element on the left and the element on the right. So here we will have an integer matches that will be equal to 0, 1 or 2. So each time when we match the left or the right element to our current element, we will increase the matches variable. And if our matches variable, if we don't have any matches, this means that our element is the unique element. So first we need to check whether we have a left element to the left, because the first element doesn't have an element to the left. So if I is greater than 0, this means that we have an element to the left. So first we check that we have an element, and after we know that we have an element, we check that array of I minus 1 is equal to array of I. Then we increase the number of matches. And also similar thing for the right side. If I is less than n minus 1, if I is n minus 2 or less, this means that we have an element to the right, and array of I plus 1 is equal to array of I. We have another match, and after doing this we just need to check the matches variable. If there are no matches, so if it is equal to 0, this means that the current element at the index I is our solution. So we can return array of I. Okay guys, and this is it. After this for loop we can just do the same as in the previous implementation. We can just return -1, which indicates that this is an invalid array. And to be consistent with the previous implementation, we can also here create a current number variable to indicate which is our current number. So it is array of I, and here we can just change array of I to current number to be consistent with the previous implementations, and everything stays the same. So to recap, we sort the array, we traverse the array. For each current number we check whether it is equal to the number to the left, whether it is equal to the number on the right. If none of those two match to the current number, we know that this is the unique number and we can return it. Let us just check this. We just change our method, and here the number 3 should be the result, and we get the number 3. Just another one, another try. Let's change this to 3. Now the number 2 should be, and yes, we have a number 2. So our solution works. What is the total time complexity and space? So here we see that everything here is O of n, because we have one loop which is O of n and just some constant comparisons and incrementations and just some basic operations inside it, where each of them is O of 1. So this for loop is O of n. But this is the bottleneck of the algorithm, because we know that the time complexity, the best time complexity for sorting algorithm is O of n log n. So our time complexity is O of n log n. But we have made an improvement in terms of space, because we don't use any extra space. Our extra space is constant. We have extra space of 1. That's it with this solution, and we have one more left, guys. Let's look at the final and the most efficient solution. And guys, we have finally arrived at our fifth and final solution, and we call this solution exclusive OR. This is because in this algorithm we will take advantage of the exclusive OR bitwise operation, and we can call this for short the XOR operations. So what is the XOR operation? If we have two numbers, A and B, which are equal, A is equal to 10 in base 10, which is equal to 1010 in base 2, B is equal to 3 in our base 10, which is equal to 0011 in base 2. Okay, so let us look how to calculate A XOR B. So we convert our numbers into binary format and put it one beneath other, and we are looking at the bit
at the same position, so the bits at the position 0, so we have 0 here and 1 here. So what will be the result? If we look at just 2 bits, the result will be true if those 2 bits are different, and the result will be false or 0 if those 2 bits are the same. So here we have 0 and result will be 1. Here we have 1 and 1, they are same, result will be 0. Here we have 0, 0, they are same, result will be 0. And here we have 1 and 0, result will be 1 because they are different. So the final solution of A XOR B is 1001 in binary, and this is the number 9 in decimal notation in the base 10. So let's explore other interesting properties of the XOR operation. So if we take the XOR with the same number, so A XOR A will be always equal to 0, because all the bits at the corresponding positions are always the same, because those two numbers are the same. This means that each bit in the result will be 0, so the total result will be 0. Another interesting fact is that A XOR 0 will always be equal to A, so the number doesn't change. So here we see that the A is 1010 and the result will be 1010. This is because if there was a bit 0 in A and there's always 0 bit in the number 0 at each position, if this is 0, the result won't change because 0 and 0 are same and the result will be 0. But here if we have as a 1 in this position, we have a 0 down there and the result will be 1 because they are different. So here we can see that A XOR 0 doesn't change anything. So 0 is an element which doesn't change the result. Similarly, like 0 is the neutral element in addition. So this also holds for XOR operation. And finally, if we look at the result of A XOR B and B XOR A, we can see that those two are the same, so it doesn't matter in which order we execute these operations. The XOR is commutative. So A XOR B and B XOR A is the same. So we will use these facts to come up with a clever algorithm. So let us switch to the editor and show how we are going to implement our final solution. Okay guys, we are back for one more solution, but before we start we want to explore those interesting properties of the XOR operation. So let us just comment this print out, because we want to print something else. So as we saw in our previous example, we have int a is equal to 10, int b is equal to 3, int c is equal to a, and this is the sign for XOR in Java. So this little caret means a XOR b. So if we print c, the result should be equal to 9 as we saw, and the result is indeed 9. Okay, now let us check the other properties. Let us check what is b XOR a to invert the order of operations, and it also should be 9, yes indeed. And let us check what is a XOR 0. 10 XOR 0 should remain 10, so it doesn't change. And finally, what if we XOR with the same number? This should be 0. Alright, so an interesting fact is what would be the result of this operation. Let us do like this, we don't need this. If we XOR 10 and 10 and 10 again, 3 times. So what do you think will be the result? Let us see. The result is 10. Why this? This is because if we take these two and calculate the result will be 0, because a XOR a is 0. And here we are left with 0 XOR a, and we know that doing an exclusive OR with 0 doesn't change the result. We know that the result will be a, which is 10. So let us do a couple of more examples. If we
take this 5 XOR 5 XOR 3 XOR 3. What will be the result? The result will be 0, because these two 5s will equal to 0 and these two 3s will equal to 0, and 0 XOR 0 is 0. But what if we invert some of those? 3 goes here and 5 goes here. What will be the result? The result will also be 0, and this is because XOR is commutative. It doesn't matter in what order do we execute the operations, A XOR B or B XOR A. We just need to see whether we have two 3s or two 5s. But if I raise one 5, so we have two 3s and one 5, the result will be 5, because the first and the last 3 will cancel each other, will be equal to 0, and we have 5 XOR 0, which is 5. And this is the magic. Now you maybe see what are we going to do in our algorithm. Let us write this again, 5, and let us say 1, 7, 1, 8, 9, 8, and 9. So here we have two 3s, two 5s, two 1s, one 7, two 8s, and two 9s. And what will be the result? Probably you've guessed. The result will be 7, because each of those other numbers will cancel each other, because there are two of them. There is an even number of occurrences, and only the number 7 has an odd number of occurrences. So it will be the only one left. So this is the magic behind XOR and our final algorithm. Let us implement this. So we have our solution number 5, and we call it XOR. So we just need to calculate the XOR of all elements in the array, and this will be the result with a little bit of magic, as we saw. So here we will write the time later and extra space complexity. Okay, so let us write the function public static int XOR. We will call it int n, and array of integers called array. So we will have an integer result where we will keep the XOR of the numbers so far. We will start at 0 because 0 is the neutral element for XOR operation, and we just need to iterate over the whole array. And in each iteration, the new result will be equal to the old result XOR the current number, but we can write this shorter as result XOR equal to array of I. And finally, we have to return the result. Believe it or not, we are done. These 1, 2, 3, 4, 5 lines. Let us check XOR. We just need to comment this out because we want to print the solution now. We run our program, and the output is number 2. And indeed, the number 2 is the only one which appears only once. Let us check one more example. We have two 2s, 1 9, 2 8s, and the number 9 should be the solution. And we have increased the length of our array to 11. We need to change this here. And let us run the program. And the output is 9, which is the correct answer. So this is it, guys. Let us just analyze the time. So it is pretty straightforward because we only have one loop which iterates to n, and the XOR operations is constant. So this means the total time complexity is O of n. And we see that we created just a couple of two integers, which is no extra space, so constant extra space. And this is the most efficient algorithms for all those 5 which we covered today. And this is why I think that algorithms and algorithmic problems are amazing. So here we wrote today around 150 lines of code. We wrote 5 different solutions, and each of those had around 15-20 lines of code.
we incrementally started with an n-squared solution. We incrementally improved it until we finally ended up with this amazing solution, which is just have a couple of lines and has total time complexity of n and doesn't use any extra space, which is amazing, guys. And this is how a lot of coding interviews look like. The interviewer gives you a problem and he doesn't expect from you to immediately write down the most efficient, the best solution for this problem. It is great if you show the process of thinking, of coming up with a brute force solution and then optimize it and then write down several solutions, mention some improvements, some corner cases and so on. So this is an incremental process that shows how are you thinking, how are you solving the problem, optimizing it until finally ending up with the best and most efficient solution. Let us just quickly recap all the solutions that we covered today. So the first solution that we covered was the brute force solution, which had a total time complexity of O of n squared, but didn't use any extra space, and it didn't have any limitations. It didn't have any preconditions, but it was too slow for big arrays. So the next solution was the counting array solution. It runs in linear time O of n, but it has really bad extra space complexity because the space depends on the range of the elements in the input array. So if you have to create an array with the length equal to the maximum number of our input array, which is bad. So this has the limitations that it works only for small range of integers, and also those integers have to be positive because we can't have negative indices in our counting array. The next solution, which was an improvement on the counting array solution, was using BST and hashing. So using a map implemented with a binary search tree or as a hash map, and those two overcome problems with space. So they don't have any limitations. They have O of n space, so linear space, and the binary search tree implementation runs in O of n log n because each call to search the map, to insert in the map is log n, but the hashing drops the log n factor in because each operation is constant, so the total time complexity is linear. Then we experimented with a sorting solution which has time complexity of n log n because of the sorting part, but doesn't use any extra space, which is good, and also doesn't have any limitations. And finally we saw that kind of magic function which used the XOR operation, bitwise operator. It runs in linear time and it doesn't use any extra space, it doesn't have any limitations, and it is just a couple of lines of code. We just need to take the XOR of all the elements in our input array. That's it, guys. This was practically an imitation of how could a coding interview look like. So thank you for watching and see you in the next video.